From the unimaginable depths of interstellar space, a mysterious traveler has begun its journey into our home, the solar system. It is a visitor of immense scale and unknown origin, a ghost from the cosmic dark, now captured in the gaze of our most powerful telescopes. This is the story of Comet 3 I/Atlas, a celestial enigma that is challenging our understanding of the cosmic neighborhood we call home. Astronomers first detected a faint, unassuming smudge of light, a whisper against the silent backdrop of the cosmos, hinting at something new. This faint signal was captured by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic sentinel scanning the heavens for potential threats. But this was no ordinary asteroid. Its trajectory was bizarre, its path unlike anything typically found orbiting our sun. It came from elsewhere. The designation 3I is a key to its identity, I for interstellar, confirming it as only the third such object ever detected by humanity. Its journey began long ago, perhaps in a star system, hundreds or even thousands of light years away from our own sun. For eons it drifted through the lonely, silent expanse between the stars, a frozen relic of a planetary system we will never see. Now, by a chance of cosmic alignment, its path has intersected with ours, offering a rare glimpse into the universe beyond our borders. The initial observations of 3I/Atlas were startling. The data suggested this object was colossal, perhaps larger than any known comet from our own system. Its nucleus, the solid core of ice and rock, was estimated to be dozens of kilometers in diameter, a true giant of the outer dark. As this interstellar guest draws nearer to our sun, the warmth of our star begins to stir it from its ancient slumber. Ices that have been frozen solid for millions, or even billions of years, are starting to sublimate, turning directly from solid to gas. This process creates the coma, a vast, glowing atmosphere of gas and dust that envelops the nucleus, making the comet visible to us. The solar wind, a constant stream of charged particles from our sun, then pushes this material away, forming its magnificent tail. But the mystery of 3I/Atlas deepens with every new observation. Its behavior is not what astronomers expected from such a large object. The comet's brightness has been fluctuating wildly, defying predictable models of cometary activity, hinting at an unstable and dynamic nature. Is it breaking apart? Is its surface experiencing violent, explosive outbursts as it awakens in the solar heat? The questions are mounting. Understanding this visitor is more than a curiosity. It is a chance to analyze the building blocks of another solar system, delivered to our doorstep. What elements does it carry? What chemical compounds are locked within its ancient ice? The answers could reshape our models of planet formation. Comets are often called dirty snowballs, but they are more accurately described as pristine time capsules from the dawn of a solar system. They preserve the original chemistry of the protoplanetary disk from which planets are born, a chemical fingerprint of its home star. By studying the light from 3I/Atlas, using a technique called spectroscopy, we can decipher this chemical fingerprint from millions of kilometers away. This allows us to compare the raw materials of its birthplace with the materials that formed Earth and our own planetary siblings. Are the fundamental ingredients for life, the complex organic molecules, universal? This comet may hold a piece of that profound answer. Its trajectory is another source of intense study. It is on a hyperbolic path, meaning it is moving too fast to be captured by our sun's gravity. This is the definitive signature of an interstellar object. It is not a member of our solar family, it is just passing through. It will make its closest approach to the sun, a point known as perihelion, before being flung back out into the interstellar void. Once it leaves, it will likely never return, continuing its solitary journey among the stars for countless millennia to come. This gives humanity a very narrow window of opportunity to study this object in as much detail as our technology will allow. Observatories around the world and in orbit are coordinating their efforts, turning their gaze towards this single fleeting point of light. The data we gather in the coming months will be analyzed for years, potentially rewriting textbooks on cometary science and solar system formation. What could have ejected such a massive object from its home system? The forces required would have been truly astronomical in scale. Perhaps a close encounter with a giant planet, like a Jupiter or Saturn, gravitationally slingshotted it into the abyss. Or maybe it was a disturbance from a passing star, disrupting the quiet architecture of its native planetary system long ago. Each interstellar object we find provides a new data point, helping us understand the chaotic dynamics that shape stellar systems across our galaxy. The discovery of three IATLAS follows those of Oumuamua and Borisov, confirming that our solar system is not an isolated island. Instead, we are part of a vast, interconnected galactic environment, with material constantly being exchanged between star systems over cosmic timescales. These interstellar visitors are the messengers, carrying tales and materials from distant stellar shores, connecting us to the wider cosmos. The name Atlas is fitting, as this discovery places a new weight of understanding and mystery upon the shoulders of the scientific community. We are witnessing a singular event, a brief intersection of our own world's story, with a much older, much longer story from afar. As the comet gets closer, its coma will expand and its tail will stretch for millions of kilometers, a spectacular celestial display. Will it survive its journey around our sun? The intense heat and gravitational forces could be enough to completely disintegrate this ancient traveler. Its fate remains unknown. Another chapter in the unfolding mystery that is 3I/Atlas, a story written in ice, rock, and light. Join us as we journey alongside this enigmatic object, exploring the science behind its discovery and what it means for humanity's place in the universe. We will analyze the data, explore the theories, and confront the profound questions that this silent messenger from the stars has brought with it. How was it formed? Where did it come from? And what secrets has it carried across the vast, silent emptiness of interstellar space? The voyage of 3I/Atlas is not just a journey of a comet. It is a journey of discovery for every one of us. The Cosmic Chronicle is being written, and this visitor is its newest, most mysterious, and perhaps most revealing entry yet. To truly comprehend the significance of 3I/Atlas, we must first contemplate the journey it has undertaken. It did not originate in the familiar cold confines of our Kuiper belt or the distant Oort cloud. Its birthplace was an entirely different star system, a place of unimaginable distance. For countless millennia, it drifted through the interstellar medium, a vast near-empty expanse between the stars, where the temperature hovers just a few degrees above absolute zero. This is a realm of profound silence and solitude, where the light from the nearest stars takes years or even centuries to cross the void. The comet was a frozen time capsule, preserving the primordial conditions of its home system, waiting for a gravitational nudge to send it on its epic voyage toward our sun. The velocity of this object is a crucial piece of evidence confirming its exotic origin. Objects belonging to our solar system follow elliptical, closed orbits, forever bound by the sun's gravity. They may swing out into the distant reaches, but they always fall back. 3I/Atlas, however, is on a hyperbolic trajectory. This is the geometric path of an object moving with such immense speed that the sun's gravitational pull can bend its path, but can never capture it. It is moving too fast to be contained. This escape velocity is the unambiguous signature of an interstellar interloper, a cosmic tourist that was never a permanent member of our celestial family, merely a transient visitor passing through on its grand galactic tour. The initial estimates of the comet's size were staggering, placing its nucleus in a category of its own. Based on its early brightness, astronomers calculated a diameter that could have been tens of kilometers, making it a true behemoth. A typical comet nucleus from our own solar system, like Halley's Comet, is only about 15 kilometers across. This immense scale suggested that 3I/Atlas might have been a supercomet, a class of object far larger and more massive than we are accustomed to seeing. Such a size would imply that its parent planetary system was either incredibly rich in the volatile ices that form comets, or that the dynamics of that system were particularly efficient at ejecting its largest primordial bodies into the interstellar void. The central mystery of 3I/Atlas began to unfold as it approached the orbit of Mars. Instead of brightening steadily as predicted by all conventional models, its light curve began to behave erratically. It would surge in brightness, then inexplicably fade. This was not the smooth, predictable awakening of a typical comet. Something far more complex and violent was occurring on its surface. The data suggested a series of localized, energetic outbursts, pockets of supervolatile ices like frozen carbon monoxide or nitrogen, being exposed to sunlight for the first time in eons. These pockets were likely flash heating and erupting into space, acting like powerful, natural jet engines that were sending the comet into a chaotic, unpredictable pattern of activity. The most dramatic and revealing chapter in the story of 3IATLAS was its subsequent fragmentation. Telescopes like the Hubble Space Telescope turned their sharp eyes towards the object and saw not one, but multiple distinct points of light where a single, solid nucleus should have been. The great interstellar giant was breaking apart. The combined stresses of its journey were proving too much. The thermal shock from the sun's increasing warmth was likely creating deep fissures within its structure, while the subtle, yet relentless, gravitational tidal forces from the sun were gently pulling it apart. The ancient bonds holding its icy and rocky components together, stable for millions of years in the deep freeze of space, were finally failing. The process of studying such a distant, faint object relies on the science of spectroscopy, a powerful tool that allows us to perform a chemical analysis from hundreds of millions of kilometers away. As sunlight passes through the coma of gas and dust surrounding the comet's nucleus, the different molecules within that gas absorb specific wavelengths of light. By capturing the reflected light with a telescope and passing it through a spectrograph, we can see this missing light as dark absorption lines. Each element and compound has a unique spectral fingerprint, a barcode written in light. This allows us to definitively identify the chemical constituents of the comet's sublimating ices, revealing the composition of a world formed around another star. Initial spectroscopic analysis of 3I/Atlas's coma began to reveal the familiar signatures of water ice, the bedrock of comets in our own solar system. However, astronomers were keenly searching for something more: the ratios of different isotopes. For example, the ratio of deuterium, a heavy form of hydrogen, to regular hydrogen can vary significantly from one stellar system to another. This ratio acts as a crucial geochemical tracer, a cosmic return address that could tell us about the specific environment in which the comet formed. Finding a ratio dramatically different from that of our own solar system's comets would be definitive proof of its exotic origins and provide clues about the chemistry of its home. One of the most profound goals in studying any comet, especially an interstellar one, is the search for complex organic molecules. These are the carbon-based compounds that are the fundamental building blocks of life as we know it. We know from studying comets in our own solar system that they are rich in these materials, including amino acids. The theory of panspermia suggests that comets could have delivered these vital ingredients, along with water, to the early Earth. Discovering a similar organic richness in 3IATLAS would provide powerful evidence that the raw materials for life are not unique to our solar system, but are instead common, distributed widely throughout the galaxy via these interstellar messengers. The physical structure of a comet's nucleus is not a solid, uniform ball of ice and rock. It is better understood as a fragile conglomerate, a loose collection of smaller icy bodies and dust, held together by their own weak gravity. This rubble pile structure is what makes them so susceptible to fragmentation. As the volatile ices sublimate, they create jets of gas that can increase the comet's rotation. If this spin-up becomes too rapid, the centrifugal forces can overcome the weak internal gravity, causing the nucleus to shed material or break apart entirely. The chaotic brightening and subsequent breakup of 3IATLAS strongly suggest it had this fragile, rubble pile composition, a common but rarely observed characteristic of cometary bodies. The coma of 3I/Atlas, the vast glowing atmosphere of gas and dust, grew to an astonishing size before the comet's disintegration. At its peak, this tenuous cloud was estimated to be larger in diameter than the planet Jupiter, a truly immense structure. Yet, this entire visible spectacle was generated by a solid nucleus that was merely tens of kilometers across. This demonstrates the incredible efficiency of sublimation in the vacuum of space. A tiny amount of solid ice, when warmed by the sun, can expand to create an atmospheric structure of planetary proportions. It is a beautiful and ghostly display, a temporary atmosphere created from ancient ice, visible across the solar system. The disintegration of 3IATLAS was not a failure of observation, but a unique scientific opportunity. As the nucleus broke apart, it exposed fresh, pristine ice from its interior to direct sunlight for the first time. This material had been shielded from the harsh radiation of interstellar space for its entire journey, representing the most unaltered sample of its home system's chemistry. The subsequent outbursts from these newly exposed surfaces provided a temporary boost in brightness and a fresh cloud of gas for our spectrographs to analyze. The comet's death throes were, in effect, its final and most revealing scientific transmission, a last gift of data before its remnants continued on their path. The existence of interstellar objects like 3I/Atlas, Oumuamua, and Borisov forces us to reconsider the solar system's environment. We tend to think of our system as an isolated island, but these discoveries confirm that it is not. There is a constant, albeit sparse, traffic of objects passing between the stars. The galaxy is a dynamic place where planetary systems are not closed boxes. They actively exchange material over billions of years. This implies that fragments of our own solar system, perhaps ancient comets ejected by Jupiter's gravity long ago, are right now journeying through other star systems, carrying the chemical signature of our own home to distant, unknown worlds. The ejection mechanism required to send a body like 3IATLAS on an interstellar journey speaks to the immense gravitational power at play during the formation of planetary systems. The most likely scenario involves a close encounter with a gas giant planet. In the early, chaotic days of its home system, the comet was likely perturbed from a stable orbit and sent on a path that brought it close to a massive planet, a world analogous to our Jupiter or Saturn. The planet's immense gravity acted like a slingshot, accelerating the comet to a speed exceeding the escape velocity of its parent star. It was flung away from its home, a gravitational exile destined to wander the galaxy. Comparing 3IATLAS to its interstellar predecessor, 2I/Borisov, reveals fascinating differences. Borisov behaved much like a textbook comet from our own solar system, just with a hyperbolic trajectory. It was active, displayed a clear tail, and its composition, rich in carbon monoxide, was familiar. 3I/Atlas, on the other hand, was an entirely different beast. Its immense initial size, its chaotic activity, and its ultimate self-destruction suggest a greater diversity among interstellar comets than previously imagined. Perhaps it came from a stellar system with a fundamentally different composition, or it represents a different class of object altogether, something that has no direct analog in our own celestial backyard. The Atlas survey that discovered this comet is a testament to the power of modern, automated sky surveys. These robotic telescopes are not looking for specific objects, but are constantly scanning the entire visible sky, night after night. They take rapid successions of images of the same patch of sky and use sophisticated software to detect anything that has moved or changed in brightness. This automated process is how we can find these faint, fast-moving interstellar visitors that would have been completely missed by earlier generations of astronomers. It is a new era of discovery, where artificial intelligence and robotics are our primary sentinels watching over the cosmic ocean. The faintness of the fragments after the breakup of 3IATLAS presents a significant observational challenge. The pieces are now far dimmer than the original unified body, pushing the limits of even our most powerful telescopes. However, tracking these fragments is crucial. By observing their individual paths, we can better model the forces that caused the breakup and refine our understanding of the nucleus's internal structure. We can also see if different fragments exhibit different behaviors, which could suggest that the original nucleus was not uniform in composition, but was instead a collection of smaller bodies with distinct chemical makeups, a celestial chimera from another star. The dust tail of a comet is different from its gas ion tail. While the ion tail is pushed directly away from the sun by the solar wind, the dust tail is composed of heavier particles that are less affected. These tiny grains of rock and dust are pushed more gently by the pressure of sunlight itself, called radiation pressure. As a result, the dust tail tends to be more curved, and often points to a location between the ion tail and the comet's orbital path. Studying the particles within this dust tail can tell us about the solid, rocky components of the comet, providing clues about the geology and mineralogy of the planetesimals that formed in its distant home system. While 3IATLAS posed no threat to Earth, its discovery highlights the importance of planetary defense surveys like ATLAS. Its trajectory was never going to intersect with our planet's orbit, but its presence is a stark reminder that the solar system is a dynamic environment. By cataloging near-Earth asteroids and comets, these surveys provide us with the crucial early warning needed to potentially mitigate a future impact threat. The same systems that can find a mysterious visitor from another star are also our best line of defense for protecting our own world, demonstrating a beautiful synergy between pure scientific discovery and the practical necessity of planetary stewardship. Future missions, like the European Space Agency's Comet Interceptor, are being designed specifically to capitalize on discoveries like this. The spacecraft will be parked in a stable location in space, waiting. When a new, pristine, long-period comet, or ideally an interstellar object, is detected on a suitable trajectory, the mission can be rapidly retargeted to fly by the object and study it up close. This would revolutionize our understanding, moving us from remote observation to direct in situ measurements of the gas, dust, and nucleus. It is a mission concept born from the realization that these interstellar visitors are a unique and fleeting opportunity for unparalleled discovery. The color of a comet's coma and tail can provide important clues about its composition. Different gases, when excited by ultraviolet radiation from the sun, glow in specific colors. For instance, the presence of diatomic carbon, C2, often results in a distinct greenish hue in the coma, while ionized carbon monoxide, CO+, can contribute to the blue color of the ion tail. By carefully analyzing the colors present in high-resolution images of 3I/ATLAS, astronomers could map the distribution of different parent molecules as they float away from the nucleus, creating a dynamic picture of the comet's outgassing process and its chemical architecture before it disintegrated. The concept of a light curve is fundamental to understanding objects like 3I/ATLAS. It is a simple graph that plots the brightness of an object over time. For a well-behaved comet, this curve should be a smooth, predictable arc, brightening as it approaches the sun and fading as it departs. The light curve of 3IATLAS was anything but smooth. It was jagged, with sharp peaks and deep troughs, indicating its unstable, eruptive nature. This graph, as simple as it seems, told the dramatic story of the comet's life and death within our solar system. It was the object's heartbeat, and it showed us the precise moment that its heart finally broke. What will become of the fragments of 3I/ATLAS? They will continue to travel along the same hyperbolic trajectory as the original parent body, fated to leave our solar system and never return. They will not, however, travel as a single, cohesive unit. The breakup event gave each fragment a slightly different velocity, so they will gradually drift apart over time. For millennia, they will travel as a ghostly, expanding cloud of debris through interstellar space. They are a funeral procession on a galactic scale, the scattered remains of a once mighty visitor, carrying the memory of their brief, violent encounter with our star back out into the great, silent dark. The study of interstellar objects provides a vital, independent test of our theories of planet formation. Our current models are based entirely on one data point: our own solar system. We assume that other systems form in a similar way, with rocky planets close to the star and icy bodies farther out. Interstellar comets, like 3IATLAS, are the first direct samples of the building materials from other systems. If their composition is broadly similar to our own comets, it supports the idea that our solar system is typical. If they are wildly different, it could mean that the galaxy is filled with a much greater variety of planetary systems than we ever imagined. The Oort cloud is the theoretical spherical shell of trillions of icy bodies thought to surround our solar system at its most distant edge, a source of our own long-period comets. For 3IATLAS to have originated from a similar structure around another star is a staggering thought. It would mean that its journey began tens of thousands of times farther from its star than the Earth is from our Sun. It would have then needed to cross the immense chasm to our own Oort cloud, a journey lasting millions of years, before finally falling inwards towards our Sun. Its appearance is a testament to the immense scale of both time and space that governs the universe. The rate of discovery of interstellar objects is increasing. Oumuamua was found in 2017, Borisov in 2019, and 3 IATLAS followed. This is not because more are suddenly arriving, but because our ability to detect them is improving so dramatically. With the advent of even more powerful survey telescopes, like the Vera C. Rubin Observatory, we expect to find many more of these objects, perhaps several per year. This will transform the field from the study of a few strange anomalies into a true statistical science. We will be able to build a comprehensive catalog of interstellar visitors, finally understanding how common they are and what they can collectively teach us about our galactic neighborhood. The legacy of 3I/Atlas is not just the data it provided, but the questions it raised. It forces us to confront the fact that comets may be more fragile and structurally diverse than we thought. It challenges our models of cometary brightening and activity, showing us that these objects can be highly unpredictable. Most importantly, it serves as a powerful reminder that the universe is constantly sending us clues about its nature, arriving as faint points of light in the night sky. The story of this comet is a perfect example of the scientific process, a discovery that leads not to simple answers, but to deeper, more profound, and more beautiful questions. The nucleus of a comet is one of the darkest objects in the solar system. Its surface is coated in a thick layer of dust and complex, tar-like organic compounds, a residue left behind after a long history of surface ice sublimating away. This dark crust is a very poor reflector of sunlight, with an albedo lower than that of asphalt. This is why it is so difficult to directly image a comet's nucleus. Most of what we see is not the nucleus itself, but the brilliant, sunlit gas and dust of the coma that surrounds it. The nucleus of 3I Atlas, despite its great size, remained an unseen heart, a black core hidden within its own vast, glowing shroud. The solar wind plays a critical role in shaping a comet's appearance, specifically in the formation of its ion tail. This stream of charged particles flowing from the sun moves at hundreds of kilometers per second. When these particles encounter the gases in the comet's coma, they ionize them, stripping away electrons. These newly created ions are now electrically charged and are captured by the sun's magnetic field, which is carried along with the solar wind. This process sweeps the ions straight back, away from the sun, forming the long, straight, and often blue-tinted ion tail, a celestial windsock showing the precise direction of the invisible flow of solar particles. Each fragment of 3I Atlas is now, in its own right, a tiny interstellar comet. They will likely continue to sublimate their remaining ices as they recede from the sun, perhaps producing their own miniature comas and tails for a time. But their small size means they will exhaust their volatile materials much faster than the original body would have. Eventually, they will become dormant, inert chunks of rock and residual ice, no longer active. They will fade back into the darkness from which they came, becoming nearly impossible to detect. They will continue their journey not as a single, magnificent comet, but as a silent, scattered fleet of cosmic ghosts. The naming convention for interstellar objects is a recent addition to astronomical nomenclature. The I in designations like 2I/Borisov and 3IATLAS stands for interstellar, a category created specifically for these visitors. The number preceding it simply indicates the order of discovery. Oumuamua was 1I, Borisov was 2I, and Atlas was the third confirmed interstellar object. The name following the designation, like Atlas or Borisov, typically refers to the discoverer or the survey responsible for the find. This simple, logical system is the official astronomical record of humanity's first confirmed encounters with messengers from other star systems, a catalog that is only just beginning. The energy released during the fragmentation of 3IATLAS was immense, but it was a quiet, cold explosion. It was not a chemical or nuclear detonation, but a mechanical failure on a grand scale. The energy came from the sun, stored as thermal stress within the comet's nucleus. It also came from the rotational momentum of the object itself. The final breakup was simply the moment when these accumulated stresses overcame the material strength and weak gravity holding the comet together. It was a silent, graceful disintegration. A slow-motion explosion that unfolded over days and weeks. A cosmic ballet of ice and rock dissolving back into the void. We must consider the possibility that objects like 3IATLAS are more representative of the galactic comet population than the comets in our own solar system. Perhaps the most massive, fragile comets are preferentially ejected from young stellar systems during their chaotic formation phase. Our own Oort cloud might be what is left over, the survivors that were not massive enough or did not have the right trajectory to be thrown out completely. If this is true, then studying these interstellar visitors is not just about seeing something exotic. It's about seeing what might be the most common type of comet in the galaxy, a class of object our own system lacks. The scientific community's response to the discovery of 3IATLAS was a masterful display of global collaboration. Within hours of its confirmation as an object of interest, observatories around the world, both professional and amateur, coordinated their efforts. A constant stream of data flowed between continents as astronomers worked around the clock to track the object as the Earth rotated. This network of shared information allowed for a much more complete picture of the comet's behavior than any single observatory could have achieved alone. It is a powerful example of how science transcends borders, uniting humanity in a shared quest for knowledge and understanding of the cosmos. The eventual fate of 3IATLAS serves as a powerful lesson in cosmic humility. Despite its immense size and the epic journey it undertook to reach us, it was ultimately undone by our star. Our sun, the life-giving center of our own world, proved to be an insurmountable obstacle for this ancient traveler. Its warmth and gravity were too powerful for the fragile structure to withstand. It is a reminder of the immense energies that govern the solar system, and the fine balance that allows worlds like our own to exist. The comet was a visitor from a gentler, colder realm, and its brief, spectacular demise was a consequence of its entry into our dynamic and violent celestial home. Could life be transferred between star systems via objects like 3I Atlas? This is the central idea of lithopanspermia. While the harsh radiation of interstellar space makes the survival of surface microbes unlikely, it is conceivable that microorganisms could be shielded deep within the interior of a large nucleus. If such a comet were to then impact a habitable planet in a new system, it could seed that world with life from its origin. The journey is long and the odds are slim, but the discovery of these interstellar travelers confirms that the transport mechanism exists. They are the potential seeds of a galactic ecosystem, connecting worlds across unimaginable distances. The trajectory of 3IATLAS did not bring it particularly close to Earth. Its closest approach was still hundreds of millions of kilometers away, posing no danger. However, its path did carry it through the inner solar system, a region populated by the rocky planets. This gave us a unique opportunity to observe how such a large, volatile, rich body behaves when it enters this warmer environment for the first time. The data gathered provides a valuable analog for understanding the early history of our own solar system, a time when countless similar icy bodies were bombarding the inner planets, delivering water and organic materials that may have been crucial for the emergence of life on Earth. The final images from the Hubble Space Telescope showed the remnants of 3IATLAS as a faint, elongated smear of light, a ghost of its former self. The individual fragments were too small and dim to be resolved clearly, having spread out into a diffuse cloud of debris. This final observation was a somber but necessary conclusion to the object's story. It was the definitive visual proof that the Great Comet was no more. The images captured the end of a journey that lasted for millions of years, a journey that, by pure chance, ended in the observational crosshairs of humanity's most powerful instruments, allowing us to witness its final, fleeting moments of existence. The amount of water ice locked within the original nucleus of 3IATLAS was likely colossal. If the initial size estimates were correct, the total volume of water could have been equivalent to one of Earth's Great Lakes, or even more. All of this water was formed in the protoplanetary disk of another star, billions of years ago. To see it sublimating into a vast cloud in our own solar system is to witness a form of interstellar weather. It is the chemistry of another world, transported across the void and released into our own, a direct and tangible link between our home and the distant, unseen planetary systems of our galaxy. The discovery of 3IATLAS has a profound philosophical impact. For all of human history, the sky has been a backdrop of familiar, predictable motions. The stars were fixed, and the planets and local comets followed regular, repeating paths. The arrival of an object from a place beyond our sun's grasp shatters this classical view. It viscerally demonstrates that we are not in a closed system. We are part of a wider, more dynamic galactic environment. The sky is not just a ceiling above our world. It is an open gateway, a thoroughfare for visitors from unknown origins, connecting our existence to the grand ongoing story of the Milky Way. What star system did 3IATLAS come from? This is perhaps the most tantalizing and difficult question to answer. By tracing its trajectory backward, astronomers can get a general direction in the sky from which it came. However, over the millions of years of its journey, the stars themselves have also moved. Our Sun and all the other stars in the galaxy are in constant orbit around the galactic center. Pinpointing the exact parent star is therefore nearly impossible. It is a cosmic cold case. The comet is a messenger with no return address, its origins forever lost to the slow, relentless dance of the stars. The cometary nucleus is not a smooth, spherical object. It is highly irregular, shaped more like a potato or a peanut. This irregular shape is a result of its formation through the gentle collision and accretion of smaller planetesimals in the early solar system. It has never been massive enough for its own gravity to pull it into a spherical shape. This irregular structure can also contribute to its chaotic behavior. As the comet rotates, different regions with varying surface compositions and topographies are exposed to the sun, leading to uneven heating and outgassing, which can cause the unpredictable jets and flares that were so characteristic of 3I/Atlas's activity. The speed at which a comet rotates is a key factor in its stability. We can measure this rotation period by observing regular patterns in its light curve as different reflective areas of the surface turn to face us. For 3/Atlas, the chaotic nature of its brightening made it difficult to determine a stable rotation period. However, it is highly likely that gas jets erupting from its surface were acting like uncontrolled thrusters, not only pushing the comet but also applying torque that caused it to spin faster and faster. This process, known as rotational spin-up, may have been the ultimate cause of its demise, the centrifugal forces simply becoming too great for the fragile nucleus to hold together. While 3IATLAS has now faded, the data collected will be analyzed for years and even decades to come. The terabytes of information from telescopes like Hubble, Atlas, and countless others hold subtle clues that are not yet apparent. Scientists will build more sophisticated computer models to try and replicate its fragmentation, testing different theories about its internal structure and composition. They will reanalyze the spectroscopic data with improved techniques, searching for trace elements and compounds that may have been missed. The physical comet may be gone, but its scientific legacy will continue to evolve, a digital ghost that will haunt and inform astronomy for a generation. Amateur astronomers played a significant role in monitoring 3I/Atlas. With modern equipment, skilled amateurs can capture high-quality images and photometric data that are incredibly valuable to the professional community. Because this global network of observers is so widely distributed, they can provide a much more continuous stream of data than a few professional observatories ever could. They were instrumental in tracking the rapid changes in the comet's brightness, providing crucial alerts and filling in the gaps in the observational record. It was a beautiful demonstration of citizen science, proving that the cosmos is open to exploration by anyone with a passion for the sky. The silence of interstellar space is profound. For millions of years, 3IATLAS moved through a near-perfect vacuum, a realm devoid of sound or weather. Its entry into our solar system was a violent awakening from this silent slumber. It was suddenly subjected to a constant sandblasting by solar wind particles and micrometeoroids. It was bathed in intense radiation and powerful gravitational forces. The deep silence was broken by the cracking of ancient ice, the roar of sublimating gas jets, and the final, graceful fracture of its entire structure. Its story is one of a journey from the most peaceful environment imaginable into one of overwhelming and ultimately destructive violence. Could there be rogue planets, worlds without a star, wandering the interstellar void alongside comets like 3I/Atlas? Theory suggests that there could be billions of them in our galaxy, ejected from their home systems just like comets. These would be incredibly difficult to detect, as they are cold and dark. However, the discovery of smaller interstellar objects confirms that the ejection process is common. These rogue planets, if they exist, would be the largest and most solitary wanderers in the cosmos. Interstellar comets may simply be the smaller, more numerous vanguard of a much larger population of galactic nomads, a hidden ecosystem of homeless worlds. The existence of 3I/Atlas and other interstellar objects has a direct impact on our search for extraterrestrial life. It means that the chemical building blocks for life are not isolated within their home systems. The galaxy is actively mixing its materials. If life did arise on another world, the raw ingredients that made it possible are not confined to that world. This galactic cross-pollination vastly increases the probability that other habitable planets will have received the necessary prebiotic chemistry. It suggests that the canvas for life is not a series of isolated dots, but a vast, interconnected web woven together by the slow, patient journeys of these interstellar travelers. The disintegration of 3I/Atlas has left behind a new, albeit incredibly sparse, meteor stream. The dust particles that were shed during its breakup will continue to travel along the comet's original hyperbolic path. This stream is not in an orbit that will ever intersect with Earth, so we will never see a meteor shower from this comet. But it exists nonetheless, a river of dust flowing through our solar system and back out into the galaxy. It is the lasting, physical trace of the comet's passage, a permanent, though invisible, monument to its brief and spectacular visit to our corner of the cosmos. The awe inspired by an object like 3I/Atlas stems from its ability to connect us to the unimaginable scales of the universe. It is a tangible object, a piece of rock and ice, that has physically crossed the void between stars. It transforms the abstract concept of interstellar space into a navigable, traversable place. Its journey took millions of years, a timescale that dwarfs human history. Yet its story unfolded in a matter of months, on a human timescale we could watch and comprehend. It is a bridge between the human and the cosmic, a visitor that reminds us of the true, breathtaking vastness of the stage on which our small existence plays out. And so, the fragments of the great interstellar comet continue their journey outwards, fading back into the darkness. They leave behind a wealth of data and a universe of new questions. Their story is a powerful testament to the dynamic, interconnected, and often violent nature of our galaxy. It reminds us that even in the silent emptiness of space, there are epic stories unfolding, journeys of unimaginable length and consequence. 3I/Atlas was more than just a comet. It was a messenger from the deep, and its brief, brilliant passage through our home has forever expanded our understanding of our place within the grand cosmic narrative. Let us delve deeper into the anatomy of this cosmic demise, beginning with the invisible yet relentless power of tidal forces. The sun's gravitational pull is not a uniform grip. It is a gradient, a force that weakens with distance. This meant that the side of 3I/Atlas facing our sun was being pulled with infinitesimally more force than the side facing away into the dark. Over vast distances, this difference is negligible, but as the comet plunged deeper into the sun's gravity well, this differential pull became a powerful stretching force. It was a silent, cosmic tug-of-war, with the sun attempting to tear the comet apart along its gravitational axis. For a loosely bound rubble pile, this constant, gentle, yet inescapable stretching was the beginning of the end. Concurrent with the gravitational assault was a war being waged within the ice itself: thermal stress. The side of the nucleus facing the sun would heat to temperatures far above freezing, while the side in shadow remained locked in the near absolute zero of deep space. This created an extreme temperature gradient, a thermal shock wave penetrating the surface layers. The ice and rock on the sunlit side would expand, while the shadowed side remained contracted and brittle. This constant expansion and contraction as the comet rotated created immense internal pressures, forming deep cracks and fissures within the nucleus. It was being weakened from the inside out, its ancient structural integrity crumbling under a thermal barrage it had never before experienced. These two forces, the tidal stretching from without and the thermal stress from within, worked in a devastating synergy. The internal cracks created by the thermal shock became the natural fault lines for the tidal forces to exploit. What might have been a survivable strain for a solid object became a catastrophic failure for a pre-weakened, fragile body. The breakup was not a single explosive event, but more likely a cascade of smaller disintegrations. One large fragment would shear off, exposing a fresh, unstable interior, which would then be subjected to the same relentless forces, leading to further fragmentation. It was a slow, graceful, and unstoppable process of celestial deconstruction, a giant falling apart piece by piece in the solar glare. We must not overlook the comet's own activity as a contributor to its destruction. As pockets of supervolatile ices like frozen nitrogen or carbon monoxide were exposed to the sun, they sublimated with explosive force, creating powerful jets of gas. These were not gentle streams, they were high-velocity eruptions from isolated vents on the surface. Because the nucleus was an irregular, tumbling body, these jets fired in chaotic directions, acting like powerful, misaligned thrusters. This introduced a significant torque, causing the comet's rotation to speed up erratically. This rotational acceleration, or spin-up, added a third executioner to the mix, centrifugal force, which further helped to pull the already stressed nucleus apart from its rotational axis. The erratic outgassing from 3IATLAS created a significant challenge for astronomers trying to predict its path. The laws of gravity are precise, but these jets introduced what are known as non-gravitational forces. They were a small but persistent thrust that subtly altered the comet's trajectory, a ghost in the machine of celestial mechanics. Accurately modeling these forces is impossible without knowing the exact size, location, and power of every jet, which is unknowable from our distance. This inherent unpredictability is a hallmark of active comets, but for an object as chaotic as 3I Atlas, it made long-term forecasting exceptionally difficult. It was a reminder that these are not just passive rocks. They are active, dynamic worlds with their own complex geology. The chemical information carried by this comet is a message in a bottle, thrown from an unknown shore millions of years ago. By analyzing the specific wavelengths of light absorbed and emitted by the gases in its coma, we can read that message. One of the first molecules identified was cyanogen, a simple compound of carbon and nitrogen. While poisonous to humans, its presence is a common and expected feature in comets. Its abundance relative to water, however, can be a crucial diagnostic tool. This ratio of cyanogen to water tells a story about the temperature and chemical conditions in the region of the protoplanetary disk where the comet originally formed, providing a vital clue to the architecture of its home system. The beautiful green glow that was observed in the coma of 3IATLAS before its breakup had a very specific chemical origin, diatomic carbon, or C2. This molecule, composed of two carbon atoms bonded together, does not exist stably on Earth, but can persist in the near vacuum of a cometary coma. When it is illuminated by the sun's ultraviolet radiation, it fluoresces, emitting light in a very specific shade of green. The presence of this C2 molecule is another piece of the puzzle. It is thought to be the breakdown product of more complex organic molecules on the nucleus's surface, offering indirect but tantalizing evidence that the comet was rich in the carbon-based compounds that form the basis of all known life. Water is the most abundant molecule in most comets, and 3IATLAS was no exception. But not all water is created equal. Astronomers are particularly interested in the ratio of heavy water, which contains the deuterium isotope of hydrogen, to normal water. This D/H ratio is a powerful cosmic fingerprint. Different parts of a young solar system have different D/H ratios, and it is thought that this ratio can vary from one star system to another. Measuring this ratio for 3IATLAS was a primary observational goal. A result that matched our own system's comets would suggest universal processes, while a radically different ratio would imply that its birthplace was a truly alien chemical environment, governed by a different history. Beyond the simple molecules, the ultimate prize is the detection of complex organics, such as amino acids. Detecting these directly from Earth is incredibly difficult. However, we can look for their simpler parent molecules, like ammonia and methane, which are known precursors to more complex biological compounds. The presence and abundance of these simpler organic building blocks in the comet's coma can be measured. Finding them in proportions similar to our own comets would strengthen the argument that the fundamental ingredients for life are not a special feature of our solar system, but are instead ubiquitous, scattered like seeds throughout the entire galaxy, just waiting for a suitable world on which to land. The dust that was shed by 3I/Atlas is as informative as its gas. Using polarimetry, astronomers can study how the dust grains scatter sunlight. This can reveal crucial information about the size, shape, and texture of the individual particles. Are they fluffy, porous aggregates, or are they solid, crystalline grains? This tells us about the way dust first condensed and clumped together in the comet's home protoplanetary disk. It is a form of remote geology, allowing us to understand the physical properties of the very first solid materials that formed planets in a solar system that we will never be able to visit, a system perhaps hundreds of light years away. The discovery of 3 interstellar objects in just a few years begs a profound question. Just how many of these wanderers are out there? The detection rate allows us to perform a cosmic calculation to estimate the density of these objects in interstellar space. The current estimates suggest that the space between the stars is not as empty as we once thought. At any given time, there are likely trillions of comet-sized interstellar objects within our Milky Way galaxy. The vast majority of these will pass by unseen, but their sheer number implies that the process of planetary system formation is surprisingly inefficient, creating and then ejecting a vast population of cosmic orphans into the galactic commons. This unseen population of interstellar nomads constitutes a kind of galactic ecology. For billions of years, star systems have been exhaling these comets and asteroids. This means that the interstellar medium is not just pristine gas and dust from the Big Bang. It is constantly being enriched with the processed materials from countless worlds. Our own solar system is, right now, moving through this ghostly rain of debris from other stars. These objects represent a mechanism for the galaxy to mix its chemical inventory over cosmic timescales. The iron in your blood may have been forged in a star that died long ago, and the water on Earth may have been delivered by comets. But 3I/Atlas suggests a deeper truth. The very atoms of distant, unknown worlds are passing right through our cosmic backyard. We must contemplate the sheer loneliness of 3I/Atlas's journey. For millions of years, it was an object in almost perfect isolation. The gravitational influence of the nearest stars would have been vanishingly small. It was a world unto itself, moving at over 100,000 kilometers per hour through a silent, empty void. There was no day or night, only the faint collective starlight of the distant galaxy. This journey represents a state of existence almost beyond human comprehension. Its arrival in our solar system was a radical and violent departure from that solitude, a sudden immersion in a dynamic environment of intense light, heat, and gravity that ultimately proved to be its undoing. The story of the discovery of 3I/Atlas is a story about the triumph of data. The Atlas telescopes generate a staggering amount of information, imaging the sky so rapidly that a human could never keep up. The initial detection of the comet was not made by an astronomer looking through an eyepiece, but by a sophisticated algorithm designed to spot faint points of light that were moving against the background stars. The object was flagged as a candidate, its position logged in a database. Only then did human astronomers step in to verify the discovery and begin follow-up observations. It is a perfect fusion of human intellect and artificial intelligence, a partnership required to find these fleeting needles in the infinite cosmic haystack. Once the alert was sounded, a global race against time began. Because 3I/Atlas was on a one-way trip, every single night of observation was precious. Astronomers from observatories in Chile, Hawaii, Spain, and elsewhere coordinated their schedules. As the Earth turned and the sun set on one observatory, another would take over, passing the virtual baton of observation across the globe. This allowed for nearly continuous monitoring of the comet during its most active and interesting phases. It was a silent, intense, and deeply collaborative effort, uniting scientists across cultures and time zones in the single-minded pursuit of understanding this unique visitor before it vanished forever. Imagine the feeling of the astronomers who first plotted its orbit and saw the unmistakable hyperbolic curve. For centuries, every comet, planet, and asteroid ever discovered belonged to our Sun. They were members of our family. To find an object whose trajectory definitively proved it came from beyond that family is a monumental discovery. It is the astronomical equivalent of a biologist finding a creature that did not evolve on Earth. It is a moment of profound paradigm shift, where the boundaries of our cosmic home are suddenly and irrevocably breached. It is the moment we realize we are not alone, not in the biological sense but in a deeper material sense. We are part of an interstellar community. This visitor has fundamentally reshaped our perspective on our own Oort cloud. We once thought of it as the edge of the solar system, a final frontier. Now we must see it differently. The Oort cloud is not a wall, it is a porous membrane, a busy border region where travelers from our system leave and travelers from other systems arrive. It is a zone of exchange, the place where our solar system physically touches the rest of the galaxy. 3IATLAS was not just an object that entered our solar system. It was an object that successfully navigated this border crossing, demonstrating that the pathways for interstellar exchange are open and active. The very existence of 3IATLAS presents a fascinating statistical puzzle. We have now seen a small, rocky, and inert interstellar object, Oumuamua, a moderately sized and active one, Borisov, and a very large, fragile, and self-destructive one, Atlas. This tiny sample of 3 already shows a bewildering diversity. It suggests that trying to define a typical interstellar object is impossible at this stage. The galaxy likely produces a vast menagerie of wandering bodies, each with a unique history and composition. Every new discovery adds another piece to this complex puzzle, gradually revealing the incredible variety of planetary systems that exist beyond our own. The ultimate fate of the atoms that once constituted 3I Atlas is a journey into infinity. The dust and gas released during its breakup are now on an escape trajectory from our solar system. The solar wind will continue to push the gas particles, while radiation pressure will gently herd the dust. This material will slowly disperse, becoming an indistinguishable part of the interstellar medium. Billions of years from now, these very atoms may be swept up into a new stellar nebula, a cloud of gas and dust that will collapse to form a new star and a new generation of planets. The material from a world in another system, after a brief visit to our own, will be recycled to build worlds yet to come. The technological leap represented by observatories like the upcoming Vera C. Rubin Observatory cannot be overstated. Its massive mirror and vast field of view will allow it to survey the entire visible sky every few nights. This will increase our detection rate of interstellar objects from 1 every couple of years to potentially several per month. We are on the cusp of a data revolution that will transform this field. We will move from studying individual curiosities to analyzing a whole population, allowing us to finally answer the big statistical questions. How many are rocky versus icy? What are their typical sizes and speeds? We are about to open the floodgates on the interstellar frontier. While 3IATLAS was breaking apart, it likely released a swarm of micrometeoroids, tiny particles of dust and ice. Spacecraft orbiting the Sun, such as solar observation probes, may have passed through this debris field. It is even possible that these tiny particles could have impacted these probes, registering as faint pings on their sensors. Scientists will meticulously search the data from these missions for any anomalous impact signals that correlate with the timing and location of the comet's disintegration. This would represent a form of in situ measurement, a direct physical sampling of the material from another solar system, a serendipitous and invaluable scientific prize. Light from 3IATLAS took time to reach us. When we observed its spectacular breakup, we were watching an event that had actually happened minutes or even hours earlier. Light, the ultimate cosmic speed limit, travels at 300,000 kilometers per second, but the distances within our own solar system are vast enough for this delay to be meaningful. This temporal lag is a constant companion in astronomy, a reminder that we are always looking into the past. Every image we captured of this interstellar visitor was a glimpse of its history, a postcard from a journey that was already further along than it appeared, its fate already sealed before its final photon message reached our telescopes. The presence of a significant dust coma around 3IATLAS suggests its surface was not pure ice. It was a true dirty snowball. The rock and dust components are crucial, as they provide the solid scaffolding that holds the nucleus together. The ratio of dust to ice is a key parameter that governs a comet's behavior. A higher dust content can create a protective, insulating crust that slows down sublimation, while a higher ice content can lead to more spectacular activity and a more fragile structure. The violent and complete disintegration of 3IATLAS suggests it may have been particularly ice-rich, lacking the sufficient rocky framework to survive its perilous journey close to our Sun. How did 3IATLAS survive its multi-million-year journey through interstellar space? This environment is not entirely empty. It is filled with cosmic rays, high-energy particles that can damage and alter material over long timescales. It is thought that over eons, these rays can create a thin, hardened irradiation mantle on the surface of an interstellar comet. This crust would have protected the pristine, volatile ices in its interior, keeping them preserved in their original state. The comet's entry into our solar system, with the sun's warmth sublimating this protective layer away, was therefore like opening a time capsule that had been sealed for millions of years. The discovery of 3I/Atlas is a profound educational moment for humanity. It provides a real-time, unfolding story of cosmic discovery that can be shared globally. It is a tangible example of the scientific method in action: observation, prediction, surprise, and new theory. It connects abstract astronomical concepts to a concrete, observable event. For a generation of students, this mysterious visitor will be their introduction to the wonders of cometary science and the scale of the galaxy. It is a story that can spark curiosity and inspire the next generation of astronomers, engineers, and scientists who will continue our exploration of this vast and wondrous universe. The scientific papers published about 3IATLAS will form the permanent record of this encounter. They are the final, distilled essence of thousands of hours of observation and analysis. These documents, filled with graphs, spectra, and orbital calculations, are the comet's official epitaph. They are where its legacy will be preserved, to be studied by future astronomers for centuries to come. The comet itself has vanished, its fragments scattered and invisible. But the knowledge it imparted, the data it gifted us, is now permanently woven into the fabric of human understanding, a ghostly but indelible chapter in our ongoing chronicle of the cosmos. We can think of the sun's gravitational field as a vast, invisible net cast into the galaxy. The vast majority of interstellar objects that encounter this net are moving too fast, and they pass right through. But our detection of several objects in recent years suggests that either there are more objects than we thought, or that our net is more effective than we realized. With every improvement in our survey technology, we are essentially making the mesh of that net finer, allowing us to catch glimpses of even smaller and fainter objects that were previously slipping through undetected. 3I/Atlas is one of our first big catches, a sign of the many more that are to come. The hyperbolic orbit of 3I/Atlas is a beautiful and elegant concept in orbital mechanics. Unlike a closed ellipse, a hyperbola is an open curve. It represents a path of eternal departure. Once an object is on such a path, it has exceeded the sun's escape velocity, and it is destined to forever move away, its speed approaching a constant value in the infinite distance. Plotting this curve for a 3IATLAS was like reading the first and last chapter of a book simultaneously. We could see where it came from, and we knew where it was going, back into the endless expanse of the galaxy. Its visit was a brief, fleeting moment, where its open path intersected with our own closed, stable world. A comet's journey is a story of constant loss. With every passage near a star, it loses a fraction of its mass as its ices sublimate away. For a periodic comet in our own system, this means it has a finite lifespan, eventually fizzling out into a dark, inert asteroid. For 3I/Atlas, its entire lifetime of significant mass loss was compressed into a few short months. It experienced an entire evolutionary arc, from a pristine, dormant body to an active comet, and finally to a cloud of debris, in a single, catastrophic encounter. we were privileged to witness the entire life cycle of a comet played out in fast forward, a dramatic and accelerated course in celestial evolution. The search for the parent star of 3I/Atlas is a fascinating detective story. By backtracking its trajectory, we can identify a patch of sky, the radiant, from which it appeared to originate. Astronomers can then look at all the known stars in that direction and calculate their past positions, trying to find a candidate star that was in the right place at the right time millions of years ago to have ejected the comet. However, the uncertainties in the comet's path and the star's motions are so large that a definitive match is highly improbable. The comet's origin remains a tantalizing mystery, a secret it took with it on its return journey to the void. The legacy of 3I Atlas will be felt most strongly in the design of future space missions. It has provided a stark, real-world example of the kind of target the Comet Interceptor mission hopes to visit. It has shown us how quickly these objects can evolve, and how crucial a rapid response is. The data from Atlas will be used to refine the mission's instruments and to develop strategies for encountering a potentially unstable and fragmenting nucleus. The ghost of this great interstellar comet will act as a guide, informing and shaping our first dedicated mission to visit a pristine relic from the dawn of another star system, ensuring we are prepared for whatever wonders we may find. Let us contemplate the materials that formed this distant traveler. The water ice was likely condensed from vapor in a vast, cold disk of gas and dust. The silicate dust grains, the rocky component, were forged in the atmospheres of long-dead giant stars and scattered through space by supernovae. The complex carbon compounds were formed by photochemical reactions, powered by the ultraviolet light of its young parent star. These separate ingredients were then brought together by gravity in a gentle, chaotic dance, forming a single, cohesive body. The comet was not just a piece of another solar system. It was a curated museum of its region's galactic history, a composite of ancient stardust and primordial ice. The event of 3I/Atlas serves to recalibrate our sense of cosmic time. The object likely existed in a stable, frozen state for a period far longer than the entire history of the human species. Its journey across the interstellar gulf was an odyssey of profound duration, yet its entire spectacular existence within our solar system, from discovery to disintegration, lasted only a few months. It is a powerful illustration of how the universe is characterized by long periods of stasis, punctuated by brief, sudden, and transformative events. We just happen to be in the right place at the right time to witness one such fleeting moment of cosmic drama. A fascinating question is whether 3I/Atlas brought with it any magnetic field. Comets are not generally thought to be magnetic themselves, but as they interact with the solar wind, a complex magnetic environment can be created around them. The ionized gas in the coma drapes the sun's magnetic field lines around the nucleus, creating a structure known as an induced magnetosphere. Studying this phenomenon from afar is difficult, but it is a key feature that a flyby mission like Comet Interceptor would investigate. This magnetic bubble, however temporary, is the comet's primary shield and interface with the stellar environment, the invisible battleground between the comet's atmosphere and the solar wind. The observation of 3I/Atlas was a multi-wavelength endeavor. Radio telescopes were used to study the specific frequencies emitted by certain molecules, providing an independent measure of the comet's chemistry. Infrared telescopes, like the Spitzer Space Telescope, could study the heat signature of the dust, revealing its temperature and composition. Ultraviolet observations, primarily from space, were crucial for studying elements like hydrogen and oxygen, which are invisible at other wavelengths. By combining all of this data, from radio to UV, astronomers could assemble a much more complete and robust model of the comet's physical and chemical state, a true holistic view of this alien visitor. We can imagine the protoplanetary disk from which 3I/Atlas was born. It would have been a vast, spinning pancake of gas and dust surrounding a newborn star. In the cold outer regions of this disk, beyond the snow line, temperatures were low enough for volatile gases like water, carbon dioxide, and methane to freeze into solid ice grains. These icy grains stuck together, gradually building up larger and larger bodies, from pebbles to kilometers-wide planetesimals. 3IATLAS was one such primordial planetesimal, a surviving building block of a planet that never was, or a planet that was, but whose gravity ultimately cast this remnant out into the great ocean of the galaxy. The forces that hold a comet together are remarkably weak. It is not a solid piece of rock, but a loose aggregate held together primarily by its own minuscule gravity, with some additional strength from the frozen ices acting as a cement. This is why they are so fragile. You could likely break a piece of a comet nucleus apart with your bare hands. It is this inherent structural weakness, so perfectly suited for the quiet calm of the outer solar system or interstellar space, that made 3IATLAS so utterly incapable of surviving the more violent conditions closer to our Sun. Its fragility was a direct consequence of its gentle, pristine origins. The breakup of 3IATLAS provides a fascinating, small-scale analog for the formation of our own solar system. In the early days, the solar system was filled with countless planetesimals like this. They were constantly colliding, breaking apart, and reaccreting. The planets we see today are the lucky few that survived this chaotic demolition derby, growing large enough to become gravitationally stable. The demise of 3IATLAS was like watching a replay of one tiny event from that primordial era, a glimpse into the violent and creative process of destruction and accretion that ultimately gave birth to the Earth and all the other worlds of our home. The light we see from a comet is almost entirely reflected sunlight. The comet itself generates no visible light of its own. It is a dark, cold object that only becomes visible because it travels into our neighborhood and is illuminated by our star. Its brilliance is borrowed glory. This simple fact carries a profound meaning. We were only able to learn about this messenger from another star because it passed through the light of our own. It is a beautiful metaphor for discovery itself. Knowledge is not created from nothing, but is revealed when the light of inquiry is cast upon the dark, unknown objects that drift into our sphere of understanding. The concept of a sphere of influence is crucial for understanding the journey of 3I Atlas. For most of its existence, it was a rogue object, not gravitationally bound to any star. As it approached our solar system, it crossed an invisible boundary, the Sun's gravitational sphere of influence, where the Sun's pull became the dominant force acting upon it. It was within this region that its path was bent and its fate was sealed. Its entire spectacular story unfolded within this bubble of solar dominance. Now its fragments are on their way out, destined to cross that boundary once more, leaving the Sun's dominion and re-entering the great democratic wilderness of interstellar space. Thinking about the origin of 3IATLAS allows us to appreciate the diversity of stars in our galaxy. Its parent star could have been a hot blue giant, a sun-like yellow dwarf, or a cool, dim red dwarf. Each type of star would create a vastly different environment for planet and comet formation. The chemical composition of the star, its metallicity, would have been inherited by the comet. By studying the comet's composition in detail, we can make educated guesses about the nature of its parent star, using the comet as a proxy to study a star we cannot see, a form of stellar archaeology through a cometary messenger. The event of 3IATLAS has permanently entered the lexicon of astronomy. For years to come, when astronomers discuss cometary fragmentation, chaotic activity, or the properties of interstellar objects, they will refer back to this comet. It has become a new benchmark, a defining case study against which future discoveries will be measured. Phrases like, "It's brightening like Atlas did before it broke up," will become common shorthand. Though its physical presence was fleeting, its conceptual presence is now permanent. It has achieved a form of scientific immortality, its name forever etched into our understanding of the cosmos. The final, diffuse cloud of debris from 3I Atlas is now receding from us at a tremendous speed. As it moves away, the light reflected from it becomes red-shifted, its wavelengths stretched by the Doppler effect. This is the same phenomenon that allows us to see the expansion of the universe in distant galaxies, but on a much more intimate local scale. This redshift will continue to increase as the fragments accelerate away from us, their light growing ever fainter and redder until they are completely lost to our instruments. We are watching its farewell in the slow stretching of light itself, a final, fading signal of its departure. We must consider the possibility that 3IATLAS was not a comet at all, but a fragment of a larger, differentiated body. If a Neptune-sized ice planet in another system were shattered by a giant impact long ago, its icy mantle could have produced a vast number of fragments. Some of these could have been ejected into interstellar space. This would make 3I/Atlas not a primordial comet, but the shard of a shattered world. This would explain its large size and perhaps its structural fragility. We were not just seeing a comet. We may have been witnessing the ghost of a destroyed planet, a refugee from a planetary catastrophe that unfolded light years away and eons ago. The journey of 3IATLAS through our solar system was a gravitational slalom. It interacted with the pull of not just the Sun, but all the planets. The immense gravity of Jupiter, in particular, would have subtly sculpted its path. Planetary scientists can use the precise trajectory of the comet to perform a kind of gravitational audit of the solar system, testing our models of where all the planets are and what their masses are. Every object that passes through provides a new test of our understanding of the celestial architecture of our home, and this interstellar visitor provided a uniquely high-speed and exotic test case. The brief, bright life of 3I/Atlas in our skies is a perfect example of a transient astronomical event. The universe is full of these fleeting moments. Supernovae that outshine their galaxies for a few weeks, gamma-ray bursts that last mere seconds, and comets that grace our skies for a few months. Modern astronomy is increasingly focused on detecting and studying these transient events, as they often represent the most energetic and transformative processes in the cosmos. Automated surveys like ATLAS are our new wide-angle eyes on the universe, allowing us to build a dynamic, real-time map of the changing heavens and catch these cosmic apparitions as they happen. The ice that composed 3IATLAS was not like the ice in your freezer. It was likely amorphous ice, a strange state of water where the molecules are flash-frozen in a disordered, glassy state rather than a neat, crystalline lattice. This form of ice is common in the extreme cold of interstellar space. As this amorphous ice is heated for the first time, it can undergo a sudden phase transition to crystalline ice, a process that releases a surprising amount of energy. This transition may have contributed to the comet's sudden outbursts and its ultimate fragmentation. It was a world built from a fundamentally different kind of ice than we are used to, a fact that may have sealed its fate. The story of 3I/Atlas is a reminder of the power of serendipity in science. No one set out to find a giant self-destructing interstellar comet. The ATLAS survey was designed to look for asteroids that might pose a threat to Earth. The discovery of this object was an unexpected and magnificent byproduct of that primary mission. It is often the case in science that the most profound discoveries are the ones we were not looking for. It is a testament to the importance of pure, curiosity-driven exploration of the universe, for we never know what astonishing wonders we might find by chance. What if we could have sent a probe to 3I/Atlas? The scientific return would have been incalculable. A mass spectrometer could have sampled the comet's gas directly, giving us a precise and unambiguous inventory of its chemical and isotopic composition. A high-resolution camera would have revealed the geology of the nucleus, its cracks, jets, and surface features in breathtaking detail. We could have witnessed its fragmentation up close. While such a mission was impossible given the short warning time, it fuels our desire to be ready for the next one. The memory of this missed opportunity will be the primary motivation for developing the rapid response capabilities we need to explore the next visitor from the stars. Ultimately, the passage of 3IATLAS leaves us with a profound sense of connection. For a brief moment, our solar system was host to a piece of another. The light reflecting from its dust and gas entered our telescopes, the data entered our computers, and the story entered our collective consciousness. Its matter did not originate here, but its story became part of ours. It demonstrated that the spaces between the stars are not barriers, but highways, and that we are part of a galactic system that is more deeply interconnected and far more mysterious than we had ever imagined. The journey of the comet has ended, but our journey to understand its message has only just begun. Let us contemplate the precise nature of the debris left in the wake of 3I/Atlas. It is not a uniform cloud, but a structured stream of particles, a celestial river of dust organized by the laws of physics. The larger, heavier dust grains, having more inertia, were less affected by the pressure of sunlight. They will travel on paths very close to the original comet's trajectory. The smaller, lighter particles, however, are pushed more effectively by solar radiation pressure. This has sorted the debris by size, with the finest dust being pushed furthest from the original path. Over time, this will create a delicate, elongated structure in interplanetary space, a ghostly fossil of the comet's passage, with its composition graded by particle size across its width. This newly formed meteoroid stream is a unique laboratory for understanding cometary structure. Each individual dust grain is a miniature sample of the comet's solid non-volatile components. If we were ever able to send a probe through this stream, an instrument called a dust analyzer could capture these particles and determine their elemental and mineralogical composition in exquisite detail. This would be the next best thing to sampling the nucleus itself. We could learn about the specific types of silicate minerals, the abundance of iron and other metals, and the nature of the complex carbonaceous materials that acted as the glue holding the comet together. The stream is a dispersed, but incredibly high-fidelity record of the comet's geology. The trajectory of this dust stream is hyperbolic, meaning it is on a one-way trip out of the solar system. This makes it fundamentally different from the meteoroid streams of comets native to our own system, like the Perseids or Leonids. Those streams occupy stable, elliptical orbits, which the Earth passes through on a predictable, yearly basis, creating our annual meteor showers. The dust from 3I Chalice, however, will cross the orbits of the outer planets and then depart into the interstellar void. It will never cause a meteor shower on Earth. It is a transient feature, a temporary river flowing through our home on its way back to the great cosmic ocean, a fleeting signature of a visitor who will not return. To truly appreciate the strangeness of 3I/Atlas, we must compare it to the first interstellar visitor, 1I Oumuamua. That object was a profound enigma of a different kind. It was small, reddish, and appeared to be completely inert, displaying no cometary coma or outgassing whatsoever. This suggested it was a rocky, asteroid-like body, not an icy one. Its light curve showed an extreme and rapid variation in brightness, leading to the controversial hypothesis that it had a bizarre, highly elongated shape, perhaps like a cosmic cigar or pancake. Oumuamua was a silent, tumbling, rocky mystery, a stark contrast to the brilliant, active, and ultimately self-destructive icy giant that was 3I/Atlas. The differences between Oumuamua, Borisov, and Atlas are a crucial lesson in avoiding cosmic generalizations. Oumuamua was rocky and inert. Borisov was a well-behaved, albeit alien, comet. Atlas was a fragile, monstrously large comet that disintegrated. If our first and only visitor had been Oumuamua, we might have concluded that interstellar objects are mostly rocky. If it had been Borisov, we might have thought they were all just like our own comets. The fact that the first three are so radically different from each other is perhaps the most important discovery of all. It tells us that the galaxy is filled with a wild and unpredictable diversity of objects, and that we should expect to be surprised with every new discovery. One of the deepest mysteries of Oumuamua was its trajectory. It exhibited a slight non-gravitational acceleration, a tiny push away from the Sun that could not be explained by gravity alone. In a comet like 3I/Atlas, this push is easily explained by the rocket-like effect of outgassing jets. But Oumuamua had no visible jets and no detectable coma. This led to a host of speculative theories, from the outgassing of unseen exotic ices to the idea that it was an object of artificial origin propelled by radiation pressure. The straightforward, albeit violent, outgassing of 3I/Atlas provides a grounding counterpoint. It shows us what a normal, non-gravitational force looks like, making the subtle, invisible push on Oumuamua seem even more strange and profound by comparison. The composition of these visitors tells a story of their origins. Oumuamua's reddish color was similar to some of the metal-rich asteroids in our own solar system, suggesting it may have been the fragment of a rocky planet's core. 3I/Atlas, with its vast quantities of water ice and volatile gases, was clearly born in the cold outer regions of a protoplanetary disk, a primordial remnant of its system's formation. This suggests that the galaxy ejects all kinds of material. The violent inner regions of planetary systems can eject the rocky cores of shattered planets, while the calmer outer regions can gently sling their icy comets into the void. We are seeing samples from every part of the planetary formation process, delivered to us from across the galaxy. The speed of these objects carries information about their home stars. An object ejected by a massive hot star system would likely have a higher ejection velocity than one from a smaller, cooler red dwarf system. Oumuamua and 3IATLAS had different incoming velocities, hinting at different origins. By building a catalog of these velocities, we can start to piece together a statistical picture of the types of star systems that are most efficient at polluting the galaxy with debris. This is a completely new field of astronomy. Galactic demographics, studied not by looking at the stars themselves, but by analyzing the planetary shrapnel they cast out into the interstellar medium over billions of years. Let us contemplate the chaotic nature of celestial mechanics. The solar system is not a perfectly predictable clockwork machine. It is a chaotic system, where tiny, imperceptible changes in initial conditions can lead to wildly different outcomes over long periods. The path of 3IATLAS through this system was a perfect illustration of this. Its trajectory was exquisitely sensitive to the gravitational pull of every planet it passed. A slightly different entry angle or speed could have resulted in a completely different path, perhaps one that brought it closer to Jupiter, resulting in a different final ejection vector. We witnessed just one of an infinite number of possible pathways it could have taken through our home. This sensitivity to initial conditions is why the origin of 3I/Atlas is so difficult to trace. To rewind its journey accurately for millions of years, we would need to know its position and velocity with impossible precision. We would also need a perfect map of the galaxy's gravitational field, including the influence of all the stars and dark matter it passed along the way. Even the tiniest error in any of these parameters would grow exponentially over the simulated journey, rendering the final result meaningless. The comet's past is shrouded in a veil of chaos, a fundamental limit to our knowledge imposed by the very nature of gravity and time. Its origin is not just unknown, it is, in a very real sense, unknowable. The gravitational influence of the Milky Way galaxy itself played a role in guiding 3IATLAS to our doorstep. Just as the Sun has a gravitational field, so too does the entire galaxy. This large-scale field creates what are known as galactic tides, a subtle stretching force that can influence the orbits of comets in the distant Oort cloud. It is believed that these galactic tides are the primary mechanism responsible for nudging comets out of their stable orbits and sending them on their long fall towards the inner solar system. For 3I/Atlas, the same force that guides the grand spiral structure of our galaxy may have been the very first, gentle push that began its epic, multi-million-year journey towards its encounter with our Sun. We can speculate about the environment in which 3IATLAS was born. Did it form in a dense star cluster, a stellar nursery like the Orion Nebula? In such a chaotic environment, young stars are packed closely together, and their gravitational interactions are frequent and violent. This would be a very efficient mechanism for stripping away the outer cometary clouds of young planetary systems and flinging their contents into interstellar space. It is therefore plausible that a disproportionate number of interstellar objects originate from these stellar nurseries. 3IATLAS may not have come from a quiet, solitary star like our Sun, but from a bustling, chaotic stellar metropolis, where planetary systems are born and disrupted in close proximity. Or perhaps 3I/Atlas came from a binary star system. These systems, where two stars orbit a common center of mass, are extremely common in the galaxy. The gravitational environment in such a system is incredibly complex and unstable. Planetesimals that form there are often on chaotic orbits, and ejections are thought to be very frequent. A close pass by the companion star could easily provide the gravitational kick needed to send a comet like 3IATLAS on its way. The chemical composition of the comet, if we could have studied it in more detail, might have held clues. The unique radiation environment from two suns could have produced a different kind of chemistry than we see in our own single-star system. Let us consider the grander journey of this object within the galactic ecosystem. The comet was ejected and began its journey. Meanwhile, the parent star itself was also moving, orbiting the galactic center at hundreds of kilometers per second. Over millions of years, the star and the ejected comet would have drifted far apart, ending up in completely different regions of the Milky Way. When 3IATLAS entered our solar system, its home star could have been on the opposite side of the galaxy. It is a profound thought. The galaxy is so vast and its motion so constant that a parent and its child, a star and its comet, can become separated by unimaginable distances, their shared origin forever erased by the slow, majestic churn of the galactic disk. The composition of 3IATLAS carries faint echoes of the galactic environment it traveled through. The interstellar medium is not a perfect vacuum. It contains trace amounts of gas, dust, and pervasive cosmic radiation. Over its long journey, the surface of the comet would have accumulated a thin veneer of interstellar dust, and its outer layers would have been processed by eons of cosmic ray bombardment. This means that the outermost layer of the comet was a composite material, a mix of its native chemistry and the chemistry of the galaxy itself. When the comet began to sublimate, it was this outer space-weathered layer that was released first, providing a potential, albeit difficult to interpret, sample of the interstellar medium. The event of 3IATLAS forces a profound shift in our cosmic perspective. We often suffer from a kind of solar system chauvinism, a bias that the objects and processes within our own home are the universal standard. This comet, by its very existence and its bizarre behavior, shatters that assumption. It is a powerful piece of evidence that our solar system is not a perfect template for the rest of the galaxy. There are other ways to build planetary systems, other outcomes, other types of worlds. It fosters a sense of cosmic humility, a realization that we are just one example among billions, and that the universe is likely far more strange, diverse, and wonderful than our limited experience has led us to believe. This newfound awareness of interstellar traffic has implications for the history of our own planet. We know the Earth has been subjected to numerous impacts over its history. We have always assumed that the impactors were asteroids and comets from our own solar system. But now we must consider the possibility that some of these past impacts could have been from interstellar objects. An impact from a high-velocity interstellar comet would be far more energetic than one from a local object. It is a remote but fascinating possibility that some of the great extinction events in Earth's history could have been triggered not by a sibling from our own celestial family, but by a high-speed visitor from a distant star. The story of this comet is, in many ways, a story about light. The faint, reflected sunlight that traveled from the comet to the Atlas Observatory in Hawaii began the story. The intense, direct sunlight in the inner solar system ended the story by destroying the comet. And the detailed analysis of that light, broken down into its constituent wavelengths through spectroscopy, is how we were able to understand the story. Light was the messenger, the executioner, and the key to unlocking the mystery. It is a beautiful demonstration of the dual role that stars play in the cosmos. They are both the illuminators that allow us to see and the powerful engines of creation and destruction that govern the fate of everything around them. The ultimate legacy of 3I/Atlas is the way it has galvanized the astronomical community. It has created a new sense of urgency and excitement around the study of interstellar objects. Research groups are forming, new observational strategies are being designed, and funding is being allocated to ensure we are better prepared for the next visitor. This single, transient event has effectively launched a new subfield of astronomy. The questions it raised are now driving a decade-long scientific quest. What was once a theoretical curiosity has become one of the most exciting and fast-moving frontiers in planetary science, all because a giant, fragile snowball from another star happened to pass our way. In the end, we are left with a feeling of profound connection to the wider universe. This object was not an abstract concept or a distant, fuzzy galaxy. It was a physical thing, a mountain of ice and rock larger than any on Earth, that traveled from there to here. It crossed the unimaginable gulf between the stars and, for a brief time, shared our solar system. Its journey connects our small, terrestrial existence to the grand, galactic narrative. It reminds us that the stars are not just distant points of light, but suns that likely have their own families of planets, comets, and asteroids. And sometimes, the members of those families come to visit. The data archive from 3I/Atlas is now a permanent digital resource for all of humanity. Unlike a physical artifact, this data can be copied, shared, and reanalyzed infinitely, without degradation. Future generations of scientists, armed with more powerful computers and more sophisticated analytical techniques, will be able to return to this data and uncover new insights that we may have missed. They will be able to test their new theories about comets against this classic, well-documented case study. The comet's physical body may have dispersed, but its informational essence has been captured and preserved, a ghost in the machine that will continue to teach us about the universe long after its last atom has left our solar system. Non-gravitational forces acting on 3I/Atlas were dramatic and obvious, but even the comets of our own solar system feel these subtle pushes. For missions that require precise navigation, like ESA's Rosetta mission, which orbited a comet, accounting for these unpredictable gas jets is a major engineering challenge. The chaotic behavior of 3I/Atlas provides an extreme case study that can be used to improve the autonomous navigation systems for future missions. By studying how its orbit deviated from a purely gravitational path, we can build more robust algorithms that will allow future spacecraft to safely orbit and even land on these active and unpredictable worlds, whether they are from our home or from another star. The shape of the coma, the comet's atmosphere, held clues to its nature. High-resolution images revealed that the coma was not perfectly spherical. It often showed fan-like or jet-like structures, pointing to specific, active regions on the surface of the unseen nucleus. As the comet rotated, these features would change, allowing astronomers to map the locations of the most volatile ice deposits. The asymmetry of the coma was a direct reflection of the asymmetry of the nucleus. It was like watching the spray from a spinning, uneven sprinkler head, allowing you to infer the shape of the sprinkler itself. It was a clever, indirect method for studying the geology of a body we could not directly see. The tail of 3I/Atlas was not just a single structure, but a complex, evolving entity. The bluish ion tail made of charged particles would often show kinks and disconnection events. These were caused by the comet flying through turbulent regions of the solar wind, where the direction or density of the sun's magnetic field suddenly changed. In essence, the ion tail acted as a giant, celestial windsock, recording the fine-grained weather of the interplanetary medium. By tracking these features as they raced down the tail at hundreds of kilometers per second, we could diagnose the state of the invisible sea of plasma that fills our solar system, using the comet as a natural probe. The story of this comet is a powerful argument for the continued funding and development of ground-based astronomy. While space telescopes like Hubble are incredibly powerful, they have a narrow field of view and their time is highly sought after. It was the wide-field, ground-based Atlas survey that found this object. And it was the global network of ground-based telescopes that provided the continuous, rapid response monitoring that was crucial for understanding its evolution. Space telescopes provide the stunning, detailed close-ups, but the tireless, all-sky scanning of our observatories on Earth is what makes those discoveries possible in the first place. They are the foundation of our cosmic awareness. Consider the perspective of the comet itself. For eons, its universe was one of stillness, cold, and near-perfect darkness, punctuated only by the faint light of distant, unchanging stars. Suddenly, a single star began to grow, becoming a brilliant, searing disk. The surface began to hiss and steam, then to erupt in violent plumes. The solid ground beneath began to crack and shift. The entire world, stable for millions of years, dissolved into a cloud of fragments in a matter of weeks. From the comet's perspective, its arrival in our solar system was a brief and utterly apocalyptic encounter, a sudden and fatal fever brought on by the proximity of our sun. Let us explore the colors within the comet's dust tail. While often appearing white to the naked eye, a comet's dust tail has a subtle reddish hue. This is because the dust particles are more efficient at scattering red light than blue light. The exact color can tell scientists about the composition of the dust. Dust rich in organic, carbonaceous compounds tends to be redder, while dust with a higher content of silicate minerals can be more neutral in color. By measuring the precise color of the dust in 3I/Atlas's tail, astronomers could make initial inferences about its rock-to-organic ratio, another clue in the grand puzzle of its formation and origin. The nucleus of 3IATLAS was likely a highly porous object, more like a packed snowball than a solid block of ice. Estimates suggest that many comet nuclei have a density less than that of water, meaning they would float. Up to 80% of their interior volume might be empty space, the voids between the loosely aggregated ice and dust grains. This incredible porosity is a relic of their gentle formation process. It is also a key reason for their structural fragility. There is simply not much solid material holding them together, making them highly susceptible to the tidal forces and thermal stresses that 3IATLAS experienced on its fatal dive towards our Sun. Before its disintegration, astronomers were searching for a specific feature in the comet's coma, an oxygen forbidden line. This is a particular wavelength of green light emitted by oxygen atoms. It is called forbidden because it is very difficult to produce in the dense conditions of Earth's atmosphere, but it is common in the near vacuum of space. The brightness of this line is a direct way to measure the rate at which water molecules are sublimating from the nucleus, as the oxygen is a breakdown product of H2O. This provides a crucial piece of data for calculating the total amount of ice the comet was losing each second, allowing us to estimate its lifespan had it survived its encounter. The pressure of sunlight, or radiation pressure, is an incredibly weak force, but over the vast scales of the solar system, it has a significant effect. It is this gentle but persistent pressure that sculpts a comet's dust tail, pushing the fine particles away from the Sun. The discovery of this force was first theorized by Johannes Kepler in the 17th century, when he observed that comet tails always point away from the Sun, but it was not fully explained until the development of Maxwell's theory of electromagnetism. 3I/Atlas, with its magnificent dust production, was a spectacular, large-scale demonstration of this subtle and elegant principle of physics, a cosmic sailing ship pushed by the faint wind of light itself. What if an object like 3IATLAS had struck Jupiter? The gas giant has long been considered the solar system's gravitational guardian, its immense gravity deflecting or absorbing many incoming comets that could otherwise threaten the inner planets. An impact of this scale would have been a spectacular event, likely creating an atmospheric disturbance far larger than the Earth, similar to the famous Shoemaker-Levy 9 impacts in 1994. It would have been a unique scientific opportunity, allowing us to study the composition of an interstellar object as it was consumed by Jupiter's atmosphere. The path of 3IATLAS did not take it close to Jupiter, but its existence is a reminder that such interstellar impact events must occur in our system from time to time. The sheer amount of data generated by the study of 3IATLAS highlights the role of big data in modern astronomy. The nightly images from survey telescopes, the high-resolution spectra from large observatories, and the long-term photometric monitoring created a dataset of immense size and complexity. Analyzing this requires powerful computational tools and sophisticated algorithms. Astronomers can now search this archive for subtle correlations and patterns that would be invisible to the human eye. The discovery was made by an algorithm, and the deepest understanding will also come from a symbiotic partnership between human scientific intuition and the brute force analytical power of machine learning, a new paradigm for cosmic exploration. Every image taken of 3IATLAS had to be carefully processed to remove the signatures of our own planet and technology. The light from the comet passed through Earth's turbulent atmosphere, which blurs and distorts the view. It was captured by electronic detectors that have their own imperfections and noise. And often, the images contain the streaks of artificial satellites passing through the field of view. A huge amount of work goes into cleaning and calibrating the raw data to produce the final, scientifically useful images. It is a hidden but essential part of the process, a digital purification ritual that allows the faint, ancient light of the visitor to be seen with pristine clarity. The story of 3I/Atlas is a powerful lesson in impermanence. The object itself likely existed for billions of years, a quiet and stable resident of the interstellar void. Its journey to our solar system was an epic of endurance, yet its entire visible, active life was compressed into less than a year. It was a fleeting apparition in our skies, a temporary spectacle that blossomed and then vanished. It serves as a cosmic memento mori, a reminder that even on astronomical timescales, things of great size and antiquity can have sudden, and definitive ends. Its beauty was inseparable from its brevity, a fleeting glimpse of another world that no human will ever see again. Could an interstellar object be captured into a stable orbit around our Sun? It is theoretically possible, but incredibly unlikely. The object would need to approach the Sun on a trajectory that passes extremely close to a giant planet like Jupiter. Then, a complex three-body gravitational interaction would have to occur, with the planet effectively absorbing the object's excess velocity and nudging it into a new, elliptical orbit. The celestial mechanics would have to be perfect. While we have not yet found any interstellar immigrants in our solar system, their possible existence is a tantalizing idea. There could be asteroids or comets in our midst that were born around another star and were captured long ago, hiding in plain sight. The passage of 3 IATLAS through the plane of our solar system, the ecliptic, was a key moment. This is the flat disk where all the planets orbit. As the comet passed through this region, it experienced the densest and most complex part of the Sun's gravitational field. It was also in this region that it received the most intense solar heating. The timing of its fragmentation, occurring as it approached the ecliptic plane, was likely not a coincidence. This was the zone of maximum stress, the final gauntlet it had to run. It failed the test, its fragile structure unable to cope with the combined gravitational and thermal assault of the solar system's heartland. One can only wonder what intelligent beings in 3I/Atlas's home system would think, if they exist. Did they watch this object being ejected from their cosmic neighborhood long ago? Do their astronomical records note a long-departed comet? And if they had the technology to track its multi-million-year journey, could they have watched in real time as it entered our solar system and was destroyed by our star? It is a fascinating, speculative thought. We were the observers of this comet's end, but its story may have had other observers at its beginning. Its journey forms a potential, albeit impossibly long and silent, bridge between our world and another. The final, fading fragments of 3 IATLAS will continue to cool as they recede from the Sun. The process of sublimation will slow and then stop completely as they cross the snow line in the outer solar system. They will reacquire a coating of frost and once again become dormant, inert bodies. Their surfaces, however, will be fundamentally changed. They will be scarred and altered by their brief, violent encounter with solar heat. They will not return to the interstellar void as pristine objects, but as veterans, carrying the physical memory of their passage through our home, a subtle chemical and geological signature of their solar encounter that they will carry with them for the rest of time. The discovery of 3 IATLAS helps us place our own solar system in a galactic context. The fact that our system is visited by these objects confirms that the ejection of planetary building blocks is a common, perhaps even universal feature of planet formation. It means our own Sun, in its youth, likely ejected its own fleet of comets and asteroids into the galaxy. Right now, there are chunks of our own solar system's primordial material traveling through other star systems. It is a humbling thought. We are not just passive observers of this galactic exchange. We are active participants. We have contributed our own messengers to the great cosmic conversation. The awe we feel when contemplating 3 I/Atlas is a deeply human response. It is a form of the sublime, an emotional reaction to something so vast in scale and implication that it challenges our everyday frame of reference. The comet's journey across light years, its immense size, and its ultimate destruction connect us to the fundamental forces that shape the universe. This feeling of awe has been shown to have a positive psychological effect, promoting curiosity, creativity, and a sense of connection to something larger than oneself. In this sense, the comet was not just a scientific object. It was a gift to our collective consciousness, a cosmic catalyst for wonder. The search for life in the universe is often focused on listening for signals or looking for biosignatures on exoplanets. Interstellar objects like 3 IATLAS represent a third and perhaps more direct path. They are physical probes from other solar systems delivered directly to us. While the chances are infinitesimally small, it is not impossible that such an object could carry with it preserved microfossils or complex organic molecules indicative of life. Every interstellar object that passes through our system must be scrutinized with this profound possibility in mind. They are cosmic lottery tickets, and while the odds of winning are long, the jackpot would be the single greatest discovery in human history. The story of 3I/Atlas is a perfect illustration of how scientific knowledge is built. It began with a single anomalous data point. This led to a hypothesis. It was an interstellar object. This hypothesis generated predictions. It would follow a hyperbolic path and might have an unusual composition. Observations were then made to test these predictions. Some, like the trajectory, were confirmed. Others, like its expected brightness, were spectacularly wrong, leading to a new discovery: its fragility and fragmentation. This cycle of observation, hypothesis, prediction, and surprise is the engine of science. It is a process of slowly peeling back the layers of mystery, not always finding the answers we expect, but always finding a deeper and more interesting reality. The naming of celestial objects is a way of imposing a human narrative on the cosmos. The official designation, 3I/Atlas, is technical and informative. But every astronomer, amateur or professional, who tracked it across the sky formed a personal connection to it. It became, for a time, a character in their lives, a protagonist in a cosmic drama. Its brightening was a source of excitement, its fragmentation a moment of genuine surprise, and even a little sadness. This humanization of the cosmos is not unscientific. It is the source of the passion that drives the science. It is the act of finding meaning and story in the cold, elegant mathematics of the universe. The energy budget of 3I/Atlas's fragmentation was driven entirely by the sun, the sunlight that warmed its surface, the solar wind that buffeted its coma, and the solar gravity that stressed its nucleus, all originate from the thermonuclear fusion reactions in our star's core. The comet's spectacular demise was powered by the same energy source that powers life on Earth. In a very direct way, the sun's energy first revealed the comet to us by illuminating it, and then destroyed it by overwhelming it. It was a stark reminder of the immense power of our star, a force of both creation and destruction, capable of nurturing a planet like Earth while simultaneously demolishing a mountain of ice from another star. Imagine holding a piece of 3I/Atlas in your hand. It would likely be a dark, almost black, piece of incredibly lightweight and fragile material. It would be colder than anything on Earth, and as it warmed, tiny jets of gas would erupt from its surface. It would smell of strange chemicals, like ammonia and formaldehyde, the scent of the primordial cloud from which it formed. It would be the oldest thing you would ever touch, a pristine relic from before the planets in its home system were even fully formed. To hold such an object would be to hold a piece of another world's genesis, a direct, physical connection to a place we can never reach. Future astronomers will have technologies we can only dream of. Perhaps they will have vast, space-based interferometers that can take a direct image of an interstellar comet's nucleus, resolving its surface features from millions of kilometers away. Perhaps they will have fleets of nanoprobes that can be rapidly dispatched to intercept these visitors, swarming around them and analyzing their properties in situ. The data from 3I/Atlas, primitive as it may seem to them, will be the historical foundation upon which their more advanced understanding is built. We are the pioneers, taking the first blurry snapshots of these messengers, paving the way for the high-definition explorers of the future. The silence of 3I/Atlas is one of its most profound characteristics. It carried no message, broadcast no signal. All of its secrets were encoded in its physics, chemistry, and motion. To understand it, we could not listen. We had to observe. We had to use the universal language of science to translate its silent story. This is the nature of our conversation with the universe. It does not speak to us in words, but in the subtle patterns of light, in the elegant curves of gravity, and in the fundamental ratios of the elements. The story of 3I/Atlas was written in this universal language, and our telescopes were the eyes that allowed us to read it. The passage of 3I/Atlas has subtly and permanently changed our solar system. It has left behind a faint, invisible stream of dust that will persist for millennia. It has deposited molecules of gas from another star into our interplanetary medium. The changes are infinitesimally small, completely negligible in the grand scheme of things. But they are not zero. Our home is now different than it was before the comet's arrival. It has been ever so slightly enriched, ever so slightly altered by this brief encounter. It is a beautiful and literal illustration of how everything in the universe is connected, constantly exchanging matter and energy in a slow, silent, and unending cosmic dance. The journey of discovery that this comet ignited in us is, in a way, a mirror of the comet's own journey. The comet traveled from a place of darkness and mystery into the light of our sun. In the same way, our understanding has traveled from a place of ignorance into the light of new knowledge. The comet's physical journey prompted our own intellectual journey. This parallel is the heart of scientific exploration. We follow these faint points of light, these mysterious visitors, not just to learn about them, but to learn about the universe as a whole. And in doing so, we are illuminated ourselves, our own inner darkness, pushed back by the light of understanding. And so the Chronicle of 3i/Atlas closes, but it is just one chapter in a much larger ongoing saga. The sky is full of wonders, and the universe is constantly sending new messengers for us to decipher. This great, fragile giant from an unknown star was a spectacular and generous teacher. It taught us about the diversity of the cosmos, the fragility of worlds, and the power of human curiosity. It reminded us that we live in a dynamic, interconnected galaxy, and that the next great discovery could be, at this very moment, a faint smudge of light just beginning its long fall towards our sun, ready to begin the cycle of mystery, discovery, and awe all over again. Let us now venture into the realm of the unseen, to the very heart of the mystery, the nucleus of 3i/Atlas. We never saw it, not as a solid, resolved object. Every image we have is of its luminous ghost, the coma. Yet, through the rigorous application of physics, we can infer its nature with remarkable confidence. Its chaotic tumbling told us it was not a sphere, but an irregular, lumpy body, a primordial relic of gentle accretion. The sheer volume of gas and dust it produced, even before its demise, spoke of a surface incredibly rich in volatile ices, far more so than typical comets from our own Kuiper belt. It was an object designed for the deep cold, an ice world whose composition was fundamentally unsuited for the warmth of our inner solar system, a lamb venturing into the lair of a lion. The surface of this unseen nucleus was likely a landscape of extreme contrasts. In the regions where jets erupted, there would have been exposed cliffs of ancient, pristine water ice and frozen carbon monoxide, brilliantly white against the blackness of space. Yet most of the surface was likely coated in a dark, reddish crust of complex organic molecules and silicate dust. This is the residue left behind by eons of faint, interstellar sunlight and cosmic ray bombardment, a process that slowly bakes the surface, creating a tar-like, insulating mantle. The violent activity we witnessed was the result of this protective crust being breached, exposing the hypervolatile materials beneath to direct sunlight for the first time in perhaps a billion years, triggering a runaway reaction of explosive sublimation. We can imagine the topography of this hidden world. It would not be a smooth terrain. It would be a rugged landscape of pits, cracks, and mesas, all sculpted by its long history. Some of the pits or depressions may have been the source of the major jets, acting like natural rocket nozzles that focused the outgassing. Deep fissures, likely caused by the thermal stresses of its final journey, would have crisscrossed its surface, marking the lines along which it would eventually fracture. It was a world that carried its entire history and the prediction of its future demise, written across its surface in a language of ice and shadow. Though we could not read this language directly, we witnessed its final, catastrophic translation in the comet's spectacular disintegration. The density of the nucleus, or lack thereof, was the key to its fate. We infer from its rapid fragmentation that it was an object of exceptionally low density, a rubble pile of the most fragile kind. It was not a single solid body, but a loose agglomeration of smaller, kilometer-sized blocks, or cometesimals, held together by their own feeble mutual gravity and cemented by sticky, frozen volatiles. This structure is a direct consequence of its formation in the calm, outer regions of its parent system, where collisions were gentle enough to build things up rather than shatter them. This gentle birth, however, was the very reason for its violent death. It was a structure built for peace that was suddenly thrust into a war zone of solar radiation and gravitational stress. Let us contemplate the interior of the nucleus. It would not have been uniform. It would have been a heterogeneous mix of different materials, a cosmic fruitcake of ice, rock, and organic dust. Different regions of the interior might have had different concentrations of supervolatile ices, like frozen nitrogen. This is because the smaller bodies that accreted to form the final nucleus would have come from slightly different parts of the protoplanetary disk, each with its own unique chemical fingerprint. As the comet broke apart, it may have exposed these different layers and pockets, which could explain the erratic, fluctuating nature of its brightening. We were not watching one comet die. We were watching a collection of smaller, diverse worlds being liberated and consumed. The heart of the nucleus would have been a pristine sanctuary, shielded from the harshness of interstellar space. Here, in the absolute cold and dark, the original chemical and isotopic ratios of its home system's nebula would have been preserved in a near-perfect state. This is the ultimate prize for planetary scientists. The tragedy and the opportunity of 3I/Atlas is that its destruction was the only way to access this material. The breakup of the nucleus was like a planetary autopsy, peeling back the outer weathered layers to reveal the unaltered primordial heart within. The final, intense bursts of light from the disintegrating comet were a transmission from this inner sanctum, a last, desperate signal from the moment of its birth. The final cascade of fragmentation was likely a runaway process. Once the first major fissure formed, the structural integrity of the entire nucleus would have been compromised. The tidal forces from the sun would have concentrated their stress at the tip of this crack, extending it deeper with every rotation. Gas erupting from within the crack would have widened it further, like a wedge being driven into the heart of the comet. The initial breakup would have exposed new, unstable surfaces, leading to more jets, a faster spin, and greater centrifugal force, which in turn would cause more fragmentation. It was a feedback loop of destruction, a chain reaction where each step in the comet's demise accelerated the next, leading to a swift and total collapse. Did 3I/Atlas have any magnetic properties? The ice and rock itself would not have been magnetic. However, it is possible that some of the dust grains it contained were rich in iron and other magnetic minerals. As the nucleus disintegrated, it would have released a cloud of this dust. Each tiny grain, moving through the sun's magnetic field, would have generated a minuscule electrical charge, a microscopic aurora. The collective effect of trillions of these grains would have been undetectable from Earth. But it represents another layer of complex physics in the comet's interaction with the solar environment. It was a world that was not just gravitationally and chemically active, but electromagnetically active in its own subtle way. The disappearance of the nucleus into a cloud of unresolved fragments represents a fundamental limit of our current observational capabilities. Even with the Hubble Space Telescope, we could not track the individual house-sized boulders that the comet likely became. We have reached the edge of our vision. This is a humbling but important moment in science. It defines the next frontier. It gives us the specific technological goals we need to strive for: telescopes with higher resolution, missions that can get closer. The ghost of 3I/Atlas's nucleus is a challenge to the next generation of engineers and astronomers, a faint, lingering target in the dark, daring us to build the machines that can finally see it. And so, the unseen nucleus of 3I/Atlas remains a world that exists now only in our computer models and our imaginations. We know it through its effects, like a subatomic particle that is only detected by the tracks it leaves in a cloud chamber. We studied its shadow, not its substance. But this indirect knowledge is a testament to the power of scientific inference. From a few faint points of light and the unwavering laws of physics, we can reconstruct the story of a world we never saw. The nucleus is gone forever, but our understanding of it, built from these ghostly echoes of data, has become a permanent part of our cosmic knowledge. Now let us turn our gaze to the most spectacular feature of any comet, its tail. For 3I/Atlas, this was a dual masterpiece, two distinct structures painting a story in the night sky. The first was the ion tail, a gossamer streamer of incandescent gas. This tail was a direct conversation with the sun. Ultraviolet radiation from the sun would ionize the gas molecules from the coma, giving them an electrical charge. These charged particles were then grabbed by the solar wind, a stream of magnetized plasma flowing from the sun at 1,000,000 miles per hour. This interaction swept the ions straight back, forming a long, narrow, and often blue-tinted tail that acted as a perfect pointer, a celestial arrow indicating the exact direction away from the sun. The ion tail was a thing of constant, shimmering change. Its structure was a direct visualization of the invisible turbulence in the solar wind. If the comet passed through a region where the sun's magnetic field was tangled, the ion tail would develop kinks and knots. If it crossed a boundary between fast and slow-moving solar wind streams, the tail could become completely disconnected, torn away from the comet, only to be rebuilt over the next few hours. To watch the ion tail of 3IATLAS was to watch the weather of space itself. It was a delicate, ethereal windsock, more tenuous than any vacuum we can create on Earth, yet stretching for millions of kilometers across the solar system. The second, and often more visually dominant structure, was the dust tail. This was a different beast altogether, governed by a different force. It was composed of tiny, solid grains of dust and rock, the non-volatile dirt in the dirty snowball. These particles were too heavy to be significantly affected by the solar wind. Instead, they were pushed by the much gentler force of solar radiation pressure, the faint but persistent momentum of photons themselves. This gentle push caused the dust to lag behind the comet in its orbit, creating a broad, curved, and often yellowish-white tail. It did not point directly away from the sun, but traced the comet's recent path, a trail of celestial breadcrumbs marking where the visitor had been. The dust tail was a museum of the comet's solid components. Each particle was a tiny piece of the geology of its home system. By studying the way this dust scattered sunlight, we could infer its properties. The subtle reddish color and polarization of the light suggested that the dust was composed of a mix of silicate minerals, similar to sand, and complex carbonaceous compounds, similar to soot. It was a mixture of the ingredients for rocky planets and the ingredients for life, all liberated together from their icy prison. The dust tail was a physical manifestation of the comet's dual nature, both a geological and a biological precursor, a flowing river of potential. The two tails, the straight blue ion tail and the curved white dust tail, often appeared simultaneously, creating a truly magnificent spectacle. They were a grand cosmic demonstration of the fundamental forces of the universe. One tail was governed by the laws of electromagnetism, the other by the conservation of momentum. They were a visual lesson in physics, painted across the sky with gas and dust from another star. The angle between the two tails, the split, changed depending on our viewing perspective from Earth and the comet's position in its orbit. Watching this angle evolve day by day was to watch the elegant, silent geometry of the solar system unfold in real time. As 3IATLAS began to fragment, its dust production increased dramatically. The dust tail grew broader and brighter, fed by the fresh material being released from the comet's disintegrating core. It became the dominant feature, a vast, luminous shroud that eventually obscured the fading remnants of the nucleus itself. In its final days, the comet effectively transformed itself into its own tail. The solid object dissolved and became a diffuse, flowing river of particles. It was a beautiful and poignant end, a kind of celestial sublimation, where the entire world gave itself over to the light, its substance becoming a final, spectacular, and fleeting trail across the heavens. The particles in the dust tail were sorted by size. The largest, heaviest grains were least affected by radiation pressure and remained closest to the comet's orbital path. The finest, smoke-sized particles were pushed the farthest. This created a subtle color and brightness gradient across the tail. If we could have flown a spacecraft through it, we would have found a highly structured environment. This sorting process, known as dust stratification, is a key tool for understanding the distribution of particle sizes that are being released from the nucleus. It is another example of how we can use the large-scale structure we can see to infer the small-scale physics we cannot. The existence of these magnificent tails is a testament to the incredible emptiness of space. The density of particles in even the brightest part of a comet's tail is far lower than the best artificial vacuum on Earth. It appears bright and substantial only because of its immense scale, stretching for millions of kilometers. If you were to fly through it, you would likely not see or feel anything. It is a ghost in every sense of the word, visible from afar but insubstantial up close. It is a cosmic illusion, a trick of sunlight and distance, a temporary atmospheric phenomenon created by a tiny solid nucleus in the vast, silent void. The very atoms that made up the tails of 3IATLAS are now on a journey of their own. The ionized gas in the ion tail will continue to be carried by the solar wind, eventually mixing with the heliosphere, the great magnetic bubble that surrounds our solar system. The dust particles will continue on their hyperbolic trajectory, slowly dispersing until their stream is indistinguishable from the background of galactic dust. The comet's visit has left a subtle but permanent mark, a faint seeding of our local space, with the matter from another star. The tails were the mechanism of this delivery, the beautiful, temporary structures that facilitated this microscopic exchange between our world and another. To witness a comet's tail is to witness a process of creation and dissolution simultaneously. The comet is dissolving, losing its substance forever. But in that process, it creates something of breathtaking beauty and immense scale. It is a perfect metaphor for many processes in the universe, from the death of a star that enriches the galaxy with new elements, to the decay of a fallen tree that enriches the soil for new life. The story of the tails is a story of sacrifice and transformation. The comet gave up its ancient, solid form, and in return it was granted a brief, glorious, and luminous existence as a transient sculpture of light and dust, a final, beautiful act in its multi-million-year existence. Let us contemplate the fundamental medium of this entire discovery: light itself. From the moment the first photons reflected from 3IATLAS reached the Atlas telescope, we have been in a conversation with the past. Depending on its distance, the light we saw could be minutes or even hours old. We were never seeing the comet as it was, but as it had been. This is a fundamental reality of our universe. The cosmic speed limit, the speed of light, imposes a delay on all information. Astronomy is not the study of the universe as it is. It is the study of the universe as it was. We are cosmic historians, piecing together the story of events whose outcomes were decided long before their light reached our eyes. The photons that reached us had traveled on an epic journey. They were born in the heart of our sun, traveled for 8 minutes to reach the vicinity of Earth's orbit, and then struck the comet. There, they were reflected, their paths altered by this encounter with a piece of another world. Then they began the long journey back towards us, carrying with them the chemical signature of the dust and gas they had passed through. Finally, they ended their journey by striking a silicon detector in a telescope, where their energy was converted into an electrical signal, a single bit in a vast ocean of data. Every piece of information we have came from these tenacious, resilient travelers of the void. The science of spectroscopy is the art of reading the story written in light. By spreading the faint light of the comet into a rainbow, a spectrum, we can see the dark lines of absorption and the bright lines of emission. These lines are a universal barcode. A specific dark line tells us, with absolute certainty, that a specific element, like sodium, is present in the coma. A bright green emission tells us that diatomic carbon is fluorescing. This technique is our Rosetta Stone for the cosmos. It allows us to translate the silent language of light into the familiar language of chemistry, to know the composition of an object millions of kilometers away with the same certainty as if we had it in a laboratory. The inverse square law is the silent antagonist in this story. This law of physics dictates that the apparent brightness of an object decreases with the square of its distance. This is why interstellar objects are so incredibly difficult to find. As 3IATLAS receded from us on its way out of the solar system, this law worked against us with brutal efficiency. With every day that passed, it became exponentially fainter. Its precious photons spread thinner and thinner across the expanding sphere of space. Our window of observation was not just limited by time, but by this fundamental geometric reality. It was a race against the unforgiving mathematics of deep space. The sunlight that destroyed 3IATLAS was also the source of its beauty. Without the sun's light, the comet would have been an invisible, dark object, passing through our system completely unnoticed. Its magnificent coma and tail were entirely powered by solar energy and composed of sunlight scattered by its dust. It was a paradoxical relationship. The very thing that made it visible was also the thing that killed it. This duality is common in the cosmos. Stars are the source of the energy needed for life, but they also emit deadly radiation. Supernovae create the heavy elements necessary for planets, but they also sterilize everything for light years around. The story of the comet and the sun is a microcosm of this cosmic balance between creation and destruction. Our ability to see the faint light of this comet is a testament to the staggering sensitivity of modern technology. The detectors in telescopes like Hubble can reliably register the impact of just a handful of individual photons. This is the quantum limit of observation. We are counting the fundamental particles of light, one by one, that have traveled across the solar system from an alien object. It is a technological achievement that borders on the magical. We have built machines that can see the faintest whispers of the universe, allowing us to capture the last, fading messages from a dying interstellar wanderer. This sensitivity is the foundation upon which all of modern astronomy is built. The polarization of the light reflected from the comet's dust provided another subtle clue. Sunlight is unpolarized, meaning its light waves oscillate in all directions. When this light reflects off a dusty surface, it tends to become polarized, with the waves oscillating preferentially in one direction. By measuring the degree and angle of this polarization, we can infer properties of the dust, such as its texture and porosity. For 3I/Atlas, the polarization data suggested a dust composed of fluffy, porous aggregates, consistent with the gentle way it formed in its home system. It is a remarkable technique, allowing us to learn about the microscopic texture of a grain of dust millions of kilometers away simply by analyzing the quality of the light it reflects. The light from the fragments of 3I/Atlas is now journeying outwards into the galaxy, carrying the story of its encounter with our Sun. For thousands of years, this light will travel, becoming ever fainter and more redshifted. An alien astronomer, in a distant star system thousands of years from now, with a sufficiently powerful telescope, could potentially detect this faint light. They would see the spectral signatures of our Sun, mixed with the signatures of the comet's own material. They could infer that a comet from one star had a close and fatal encounter with another. The light from this event has become a permanent, expanding monument, a spherical shell of information broadcasting the story of the comet's visit to any civilization that has the eyes to see it. We must also consider the light we cannot see. 3I/Atlas was observed in visible light, ultraviolet, and infrared, but it also likely emitted faint radio waves and even X-rays. X-rays can be generated when the fast-moving particles of the solar wind collide with the neutral gas in the coma in a process called charge exchange. These emissions are incredibly faint, but they have been detected from other comets. Missions like the Chandra X-ray Observatory may have looked at 3I/Atlas, searching for this high-energy signature. Seeing the universe in these other colors provides a more complete picture of the complex, high-energy physics that occurs when a celestial body interacts with a star. In the end, the entire story of 3I/Atlas is a narrative written in light. Its brightness told us of its size and its activity. Its light curve told us of its instability and its demise. Its spectrum told us of its composition and its origins. And its final, fading light tells us of its departure into the infinite dark. Our relationship with the cosmos is mediated entirely through this single, elegant medium. We are beings made of stardust, living on a planet illuminated by a star, who use the light from other stars to understand our place in the universe. Light is the beginning, the end, and the substance of our entire cosmic story. The discovery and subsequent study of this interstellar visitor was a profoundly human endeavor. It was not the work of a single person or a single nation, but a seamless, global collaboration of thousands of individuals. It began with the engineers who designed and built the robotic Atlas telescopes. It was carried forward by the software developers who wrote the algorithms that sifted through the nightly data deluge. The alert was then picked up by professional and amateur astronomers on every continent, who turned their instruments, their life's work, towards this single, faint smudge of light, each contributing a small piece to the giant, emerging mosaic of understanding. This global cooperation is the unsung hero of the story. There is no central authority that commands astronomers what to observe. This collaboration happens organically, driven by a shared passion for discovery. When the nature of 3IATLAS became clear, observation requests were sent, mailing lists buzzed with activity, and data was shared freely and openly across international borders. It is a model of how humanity can work together to achieve a common goal. For a few months, the political divisions on our small planet seemed to dissolve, replaced by a unified global community focused on one single, shared objective: to understand the messenger from the stars. The role of amateur astronomers in this story cannot be overstated. With access to increasingly sophisticated near-professional grade equipment, this dedicated community provided a constant stream of high-quality data, particularly on the comet's rapidly changing brightness. While large professional telescopes have their time scheduled weeks in advance, a skilled amateur can respond to an alert in minutes, capturing crucial moments of an outburst or flare that would otherwise be missed. They are the flexible, rapid response network of global astronomy, the essential connective tissue that fills the gaps in our professional observational capabilities, driven by nothing more than a pure love for the night sky. The scientific process itself was on full display. Initial hypotheses about the comet's size, based on early brightness, were made. These were published, debated, and then spectacularly revised when the comet failed to brighten as predicted and began to fragment. This is not a failure of science. It is the very essence of it. Knowledge is provisional, a series of increasingly accurate approximations of the truth. The story of 3IATLAS was a real-time lesson in how science works, with the global community collectively changing its mind based on new evidence, a beautiful and powerful demonstration of the self-correcting nature of the scientific method. The vast amounts of data were processed and are now stored in publicly accessible archives, such as the Mikulski Archive for space telescopes. This open data policy is a cornerstone of modern astronomy. It ensures that the discoveries made by multi-billion-dollar, publicly funded instruments are not the private property of a small group of scientists. Any student, any citizen, any researcher from anywhere in the world can download the raw data from Hubble's observations of 3IATLAS and conduct their own analysis. This democratization of data accelerates the pace of discovery and ensures that the legacy of this comet belongs to all of humanity, now and for generations to come. This event also highlights the deep, synergistic relationship between observation and theory. The observers, using the telescopes, provided the raw data, the what. The theorists, using computer models and the laws of physics, provided the interpretation, the how and the why. Theorists would build models to explain the comet's strange light curve, which would then make predictions that the observers could test with new measurements. This constant feedback loop, this dialogue between what we see and what we understand, is the engine that drives our knowledge forward. 3IATLAS was a perfect subject for this process, a mysterious object that pushed both our observational capabilities and our theoretical understanding to their limits. The story was communicated to the public with incredible speed and clarity. Press releases from NASA and ESA, articles in popular science magazines, and countless videos and posts by science communicators brought the unfolding drama to millions of people. This was not a discovery confined to the ivory tower of academia. It was a shared, global event. It allowed the public to participate in the thrill of discovery, to feel the surprise of its fragmentation, and to contemplate the profound implications of its existence. This act of translation, from technical data to human story, is a vital part of the scientific endeavor, ensuring that the wonders of the cosmos are not just discovered, but are truly shared. The very existence of a program like the Asteroid Terrestrial Impact Last Alert System is a sign of our species' growing maturity. We are the first generation of life on Earth that has the awareness and the capability to look up and defend itself from a potential cosmic impact. The Atlas survey, while searching for these threats, is also a machine for pure discovery. 3IATLAS posed no threat, but its discovery within a planetary defense survey is a beautiful example of the dual nature of scientific infrastructure. The same tools we build to ensure our survival also inevitably expand our intellectual and spiritual horizons, revealing a universe far grander and more mysterious than we ever imagined. The human desire to explore, is written into this story. While we could not physically send a mission to 3I Atlas, every telescope turned in its direction was an extension of our senses, a robotic proxy for our innate curiosity. We are a species that has always looked beyond the horizon. For millennia, that horizon was a mountain or an ocean. Today, it is the interstellar void. The intense, global focus on this one faint point of light was a demonstration of this ancient, unwavering human impulse to know what lies beyond the boundaries of our own small world. It is the same spirit that drove the first mariners across the sea, and it is the spirit that will one day carry us to the stars. And so, humanity's collective encounter with 3I Atlas becomes a story about ourselves. It reflects our intelligence and our ability to build the tools to see it. It reflects our collaborative nature and our ability to work together to understand it. And it reflects our deepest, most noble quality, our unquenchable sense of wonder. The comet was a mirror. In its faint, reflected light, we saw not just the chemistry of another world, but also a reflection of the best aspects of our own. It was a catalyst that brought out the curious, cooperative, and contemplative nature of our species on a global scale. We are left, in the end, in a state of contemplative calm. The frantic race to observe the comet is over. The dramatic events of its breakup have passed. What remains is the quiet, profound, and permanent change in our understanding of the universe. We now know, not as a theory, but as an observed fact, that our solar system is not an island. It is a port of call on a vast galactic ocean, and visitors from other shores will, from time to time, make landfall here. This knowledge changes everything. It reframes our home as a place of both shelter and connection, a quiet harbor in a galaxy teeming with travelers. The story of 3I Atlas induces a sense of deep time. Its journey lasted for millions of years, a span that makes all of recorded human history seem like the briefest of moments. It was born in a nebula that has long since dispersed, around a star that is now in a completely different part of the galaxy. It is a physical link to a past so remote it is almost mythological. To contemplate its journey is to stretch our minds across the eons, to connect our fleeting existence to the slow, grand, and eternal rhythms of the cosmos. It is a humbling and deeply centering experience, a form of meditation on the vastness of eternity. This encounter has sown the seeds of future discovery. The questions raised by 3I Atlas about its fragility, its composition, its origin, are now the primary scientific drivers for a new generation of telescopes and space missions. The memory of this event will fuel innovation for decades. The children who watch news reports about this mysterious visitor are the students who will one day design the probes that will intercept the next one. The comet's physical presence may have been transient, but its intellectual and inspirational legacy will be long-lived, a catalyst for a future of exploration that will go far beyond what we can currently achieve. The comet's passage leaves us with a feeling of cosmic kinship. We are made of the same fundamental stardust as this visitor. The water in its icy nucleus is the same H2O that fills our oceans. The carbon in its organic molecules is the same carbon that forms the basis of our own bodies. Its journey from there to here was not a journey of something completely alien, but a journey of a distant cosmic relative. It is a profound reminder of the universality of chemistry and physics. The laws that governed its formation around another star are the same laws that govern the formation of our Earth. We are all, truly, children of the cosmos. This story instills a sense of profound gratitude. Gratitude for living in an age where we have the technology to witness such an event. Gratitude for the thousands of scientists and engineers whose dedicated work made this discovery possible. And gratitude for the universe itself, for its capacity to produce such wonders and, by pure chance, to send one on a trajectory that intersected with our own brief moment in time. We were incredibly lucky to have been here to see it. It was a fleeting, unrepeatable celestial event, a gift from the cosmos, a spectacle of immense beauty and profound scientific importance that we were privileged to observe. The final state of the comet's remains is a return to simplicity. It began as a vast, complex cloud of gas and dust. This cloud collapsed to form a star and a disk. In that disk, complexity arose as simple ices and dust grains accreted into a large, structured nucleus. For billions of years, it held this complex form. Then, in its encounter with our Sun, all of that structure was undone. It was disintegrated back into a simple, diffuse cloud of gas and dust, destined to mix back into the interstellar medium from which it first came. It is a perfect, cosmic life cycle, a journey from dust to world, and back to dust again, a beautiful and complete story of return. We are left with the silence. The comet has gone. Its light has faded from our skies. The flurry of scientific activity has calmed. What remains is a deeper, more resonant understanding of the silent, vast, and interconnected space in which we live. The universe did not shout its secrets at us. It whispered them in the faint light of a fragile, disintegrating visitor. Our task was to build instruments sensitive enough to hear that whisper, and to be quiet enough ourselves to contemplate its meaning. The silence that follows the departure of 3I Atlas is not an empty silence. It is a silence filled with new knowledge and a profound, quiet sense of awe. The story of 3I Atlas ultimately becomes a part of our own story. It is now woven into the fabric of human knowledge, a new chapter in our species, long and ongoing quest to understand the universe and our place within it. It is a story we will tell our children, a modern myth founded on scientific truth. A tale of a giant visitor from a faraway star who came to visit us, put on a spectacular, brief display, and then vanished back into the night. It is a story of mystery, of discovery, and of our ability to comprehend the incomprehensible. It has enriched our culture just as its atoms have enriched our solar system. Let the wonder of this encounter settle. A piece of another solar system, born billions of years ago and hundreds of light years away, a world larger than a mountain, traveled for millions of years through the silent frozen void. By a chance of unimaginable improbability, its path intersected with ours. We saw it, we studied it, we watched it die, and, in its death, we learned a part of its story. This single event connects us to the entire galactic neighborhood. It is a reminder that the universe is not a static diorama, but a living, breathing, dynamic system that is constantly in motion, constantly changing, and constantly revealing new and unexpected wonders to those who take the time to look up. And so, we conclude our journey with this mysterious traveler. The legacy of 3I/Atlas is not one of fear or threat, but one of profound insight and expanded perspective. It has left us with more questions than answers, and that is its greatest gift. For it is in the pursuit of these new questions that we will chart the future of our exploration of the cosmos. The universe is a place of infinite mystery, and we are just beginning to read the first few pages of its great chronicle. The story of this comet was a glimpse at one of those pages, a beautiful, fleeting, and unforgettable chapter in the grand, silent, and awe-inspiring story of everything